Close your eyes for a moment and try to locate yourself. Not your body. That part is easy enough. You can feel the weight of your limbs, the pressure of whatever surface holds you, but try to find the thing that is doing the feeling. Try to locate the observer behind your eyes, the presence that calls itself I. You will find that no matter how hard you search, you cannot pin it down. It seems to hover just behind your thoughts, watching. But when you turn to look at it directly, it dissolves like fog in morning light. This experience, this strange inability to catch yourself in the act of being yourself, has haunted philosophers for millennia. But in the late 20th century, a physicist with a Nobel Prize and an anesthesiologist who had spent decades putting consciousness to sleep decided that this mystery was not just philosophical. They believed it was physical, measurable, and stranger than anyone had dared to imagine. The physicist's name is Roger Penrose. In October 2020, he received a phone call from Stockholm informing him that he had won the Nobel Prize in Physics for proving that black holes are an inevitable consequence of Einstein's general relativity. He was 89 years old. The work being honoured was half a century old. Elegant mathematics showing that when enough mass collapses into a small enough space, space-time itself must cave inward, creating a singularity from which nothing can escape. It was unassailable work, but Penrose did not consider it his most important contribution to science. For the past 30 years, he had been pursuing something far more controversial, something that had earned him ridicule from colleagues, dismissal from neuroscientists, and the kind of skeptical sighs that greet anyone who dares to connect the word quantum to the word consciousness. He believed that the mind, that elusive thing you just tried to find behind your eyes, operates according to principles that no classical computer can ever replicate. He believed that human thought, creativity, mathematical insight, the very experience of being aware depends on quantum mechanical processes unfolding inside structures so small they make a virus look like a mountain range. And he believed that when you die, something may persist that neuroscience cannot account for. His collaborator's name is Stuart Hameroff. An anesthesiologist at the University of Arizona, Hameroff had spent his career studying what happens when consciousness vanishes. Every time he administered anesthesia, he watched a human being disappear. The lights went out. The person who had been speaking and thinking and fearing simply ceased to be present, while the body continued its mechanical functions. The brain kept firing, the heart kept beating, the cells kept metabolizing. But the self was gone. Where did it go? And when the anesthesia wore off, where did it come back from? Together, Penrose and Hameroff developed a theory they called orchestrated objective reduction, OR for short. It proposes that consciousness arises from quantum computations occurring inside tiny structures called microtubules, which form the internal scaffolding of neurons. These microtubules, the theory claims, maintain quantum coherence long enough for quantum superposition states to collapse in a specific way, a way that Penrose believes is connected to the fundamental geometry of the universe itself. If they are right, your mind is not simply what your brain does. Your mind is what your brain accesses, a window into the quantum structure of reality, a receiver tuned to frequencies that matter and energy alone cannot explain. If they are wrong, they have wasted 3 decades chasing a beautiful mirage. Tonight, we are going to follow this idea all the way down. We will begin with the problem that started everything, the hard problem of consciousness, the question that has no agreed-upon answer despite thousands of years of trying. We will trace the path that led a mathematician obsessed with the limits of computation to believe that the mind cannot be a machine. We will enter the microscopic world of the neuron and discover structures that classical biology dismissed as mere scaffolding until a handful of researchers began to suspect they were something more. We will confront the deepest objection to OR, the claim that the brain is too warm, too wet, too noisy for quantum effects to survive, and examine the recent experiments that have thrown that objection into doubt. And we will end in a place few documentaries dare to go. The question of what happens to consciousness when the brain stops functioning, and whether OR offers any coherent account of what we might call a soul. This is not a story about certainty. The theory may be wrong. Many scientists believe it is, but it is being taken seriously enough that experiments are now being designed specifically to test it. And the man who proposed it, the man who proved that black holes must exist, believes it is the most important work of his life. If you find these slow, patient journeys through difficult ideas helpful, consider tapping that like and subscribe button. It costs nothing and helps these explorations reach others who might be lying awake with the same questions. Now, let us begin. The hard problem of consciousness has a name because a philosopher named David Chalmers gave it one in 1995. But the problem itself is older than philosophy. It is the problem you encounter every time you stub your toe. The pain is not puzzling in the mechanical sense. Nerve signals travel up your leg, reach your spinal cord, propagate to your brain, trigger activity in specific regions associated with pain processing. This sequence can be mapped, measured, even predicted. But none of this explains why it hurts. None of this explains why there is something it is like to be you stubbing your toe in that moment of sharp, unwelcome sensation. The signals are electrical and chemical. The experience is neither. The experience is what, exactly? Philosophers call it qualia, the felt quality of subjective experience, the redness of red, the sharp, bright taste of lemon, the particular ache of a minor heartbreak. Stop and feel the weight of that gap for a moment. On one side, you have brain activity, neurons firing, neurotransmitters diffusing across synapses, patterns of activation rippling through cortical tissue. All of this is third-person, objective, measurable. You could, in principle, build a machine that reads out every electrical impulse in a brain and prints the results on a scroll. On the other side, you have experience, the first-person fact that there is something it is like to be you right now, reading or listening to these words, feeling perhaps a slight drowsiness, noticing the texture of the pillow beneath your head. This is subjective, unmeasurable by any instrument yet devised, known only to you. The hard problem is explaining how one becomes the other. How does electrochemical activity, which is, after all, just the movement of charged particles, give rise to the felt sense of being alive? Not the information processing, not the behavioural outputs, not the ability to report on your own states. Those are what Chalmers calls the easy problems, not easy in practice, but easy in principle, because they can be solved by identifying mechanisms. The hard problem is different. It asks why there is experience at all. Why isn't the brain just a biological computer, processing inputs and producing outputs in the dark, with no inner light of awareness? Most neuroscientists today adopt a position called physicalism, the view that consciousness is entirely produced by the brain. Consciousness, on this view, is what the brain does when it reaches a certain level of complexity. Somehow, from enough neurons wired in the right way, awareness emerges. This somehow is doing an enormous amount of work, because no one has explained the mechanism. No one has shown how any arrangement of matter could generate subjective experience. The explanatory gap remains as wide as it was when Descartes first drew a line between res cogitans, thinking stuff, and res extensa, extended stuff. The terms have changed. The mystery has not. Penrose came to this problem from an unusual direction. He was not a neuroscientist, not a philosopher of mind, not even a biologist. He was a mathematical physicist, one of the most celebrated of the 20th century. His early work was in general relativity, collaborating with Stephen Hawking on the singularity theorems that earned him the Nobel Prize decades later. But his interests ranged far beyond gravity. He made fundamental contributions to the geometry of impossible figures, to the mathematics of aperiodic tiling, to the structure of space-time at the quantum level. He was the kind of thinker who could hold multiple vast domains in his head simultaneously and see connections others missed. In the 1980s, Penrose became fascinated by a question that had nothing obvious to do with physics. What is the relationship between mathematical truth and the human mind? The question had a specific trigger. In 1931, a logician named Kurt Gödel had proven something remarkable. Gödel showed that any consistent formal system capable of expressing basic arithmetic must contain true statements that cannot be proven within the system. This is the famous incompleteness theorem. It means that mathematical truth outstrips mechanical proof. There are things that are true which no algorithmic process following fixed rules can ever demonstrate. Penrose brooded on this result for years. He noticed something that disturbed him. Human mathematicians can recognize the truth of Gödel sentences, the very statements that are unprovable within a formal system. We can step outside the system and see that the statement is true. But a computer, running strictly algorithmic processes, cannot do this. The computer is trapped within its formal system. The human mind is not. What does this mean? Penrose concluded that the human mind cannot be a classical computer. It cannot be merely algorithmic. Whatever it is that we do when we understand mathematical truth, when we grasp the meaning of a theorem, when we experience insight and certainty, it is not computation in the Turing machine sense. The mind does something that no digital computer, however powerful, can replicate. This was, and remains, a controversial claim. Many philosophers and computer scientists reject it. They argue that Penrose misunderstands Gödel, or that human mathematical intuition is itself a kind of computation that merely appears non-algorithmic. The debate continues, but Penrose was convinced, and if the mind is not a computer, then what is it? What kind of physics could support non-computational processes? This is where the story takes its strange turn. Penrose looked at the landscape of physics and saw only one domain where something genuinely non-computable might occur: quantum mechanics. Specifically, the process by which a quantum system in a superposition of states collapses into a single, definite state upon measurement. This process, sometimes called wave function collapse, has never been fully explained. In standard quantum theory, the collapse is either ignored, you just calculate the probabilities and move on, or interpreted in various ways: many worlds, pilot waves, decoherence-based approaches. But Penrose noticed that none of these interpretations actually explained what physically happens when a superposition resolves. The mathematics describes probabilities. It does not describe the moment of choice. Penrose proposed that wave function collapse is not just an interpretive problem. It is a real physical event that occurs when a certain threshold is reached. That threshold, he suggested, is related to gravity. When a quantum superposition involves a difference in the gravitational field, when the two superposed states have slightly different space-time curvatures, the universe cannot sustain the ambiguity indefinitely. At a critical point, the superposition spontaneously reduces to one state or the other. This is objective reduction. The collapse happens on its own, not because of measurement or observation, but because of the geometry of space-time. And here is the key claim. Penrose believes this objective reduction is non-computable. The outcome is not determined by any algorithm. It is influenced by something deeper, something related to the Platonic structure of mathematical reality itself. Let that settle for a moment. If Penrose is right, then the universe contains a built-in source of non-algorithmic behaviour, the gravitational self-collapse of quantum superpositions. And if the human mind is also non-algorithmic, if our capacity for mathematical insight cannot be reduced to computation, then perhaps the two are connected. Perhaps consciousness exploits precisely this feature of quantum mechanics. But where in the brain would quantum effects be relevant? The brain is warm, biological, chaotic. Quantum coherence, the delicate property that allows particles to exist in superposition, is famously fragile. It survives in laboratory conditions at temperatures near absolute zero, in isolated systems shielded from environmental interference. The brain is 37 degrees Celsius, packed with water molecules that jostle and vibrate, suffused with electromagnetic noise from 100 billion neurons firing in overlapping rhythms. The standard view is that any quantum coherence would be destroyed in femtoseconds, trillionths of a trillionth of a second, far too fast to have any effect on thought or consciousness. This is where Stuart Hameroff entered the story. Hameroff had been thinking about consciousness from the bottom up since the 1970s. As a young anesthesiologist, he had been struck by a simple observation: general anesthetics work. Drugs as chemically diverse as ether, chloroform, halothane, propofol and xenon gas all produce the same result: the reversible loss of consciousness. But no one knew why. The brain keeps functioning under anesthesia. Neural activity continues, yet the person disappears. Hameroff noticed that these diverse anesthetics shared one property. They all interact with certain structures within cells. Specifically, they seem to bind to hydrophobic regions of proteins, oily pockets where water cannot penetrate, and the most prominent protein structures containing these hydrophobic pockets were microtubules. Microtubules are cylindrical scaffoldings inside cells. They are made of a protein called tubulin, which exists in two conformational states. Let's call them A and B. Each microtubule is a hollow tube about 25 nanometers in diameter, composed of 13 columns of tubulin dimers arranged in a helical lattice. They are everywhere in the body. Every cell uses them for structural support, for transport of cargo, for the mechanics of cell division. In neurons, they are particularly abundant, forming the internal skeleton of axons and dendrites, the long projections that carry signals to and from the neuron's body. For decades, biologists treated microtubules as passive infrastructure, scaffolding, railroad tracks for molecular motors to walk along. But Hameroff suspected they were something more. He looked at the tubulin dimers that made up microtubules and saw a candidate for computation. Each dimer could exist in one of two conformational states. The dimers were arranged in a regular lattice. They influenced their neighbours through electrical and mechanical coupling. In principle, this structure could process information, not through neural firing patterns, but through cascades of conformational changes within the microtubule itself. It would be a kind of computation happening beneath the level of the synapse, inside the neuron. But Hameroff went further. He noticed that the hydrophobic pockets within tubulin, the same pockets where anesthetics seem to bind, were regions where quantum effects might survive. Hydrophobic regions are shielded from water. Water is the great destroyer of quantum coherence because its constant molecular jostling provides the environmental noise that causes superpositions to decohere. But in a hydrophobic pocket, this noise might be reduced. Quantum states might persist long enough to matter. Hameroff proposed that tubulin dimers could exist in quantum superpositions of their conformational states, simultaneously A and B, until something caused them to reduce to one or the other. The information processing in microtubules would not be classical computation, it would be quantum computation. When Hameroff encountered Penrose's work in the late 1980s, he saw a perfect fit. Penrose needed a site in the brain where quantum processes could occur. Hameroff had one. Penrose needed a mechanism for non-computable collapse. Hameroff's microtubule model, if combined with Penrose's objective reduction, might provide it. In 1992, the two men met. By 1994, they had published the first version of orchestrated objective reduction. The name encodes the key claims. Objective reduction is Penrose's gravity-induced collapse of superpositions. Orchestrated refers to Hameroff's proposal that microtubules coordinate their quantum states, that the dimers do not collapse randomly, but in a synchronized pattern guided by the geometry of the microtubule lattice. This orchestration, they suggested, is what produces a unified conscious experience rather than a chaos of disconnected micro-events. Picture it like this. Imagine millions of tubulin dimers across thousands of microtubules in a single neuron, each dimer in a superposition of states. These superpositions are entangled, connected in such a way that they must collapse together. The quantum state evolves, explores a vast space of possibilities simultaneously. Then, when a critical threshold is reached, when the gravitational self-energy of the superposed states crosses Penrose's reduction limit, the entire system collapses at once. A moment of conscious experience occurs. This is not consciousness as an emergent property of complex computation. This is consciousness as a fundamental feature of reality, built into the quantum gravitational structure of the universe, accessing itself through the delicate architecture of biological microtubules. Let me try once more to give you a feel for that. On the standard view, consciousness is what happens when a brain gets complicated enough. It is an output, a side effect, an epiphenomenon that evolution stumbled into because it somehow helped survival. On offshore, consciousness is an input. It is already out there, woven into the fabric of space-time itself, and the brain is an antenna, a receiver tuned to pick up conscious experience from the quantum level of reality. The difference is not subtle. If consciousness is an output, then when the brain dies, consciousness simply ends. There is nothing to continue. The process that generated awareness stops, and awareness stops with it. But if consciousness is mediated rather than generated, if the brain is a window rather than a factory, then the question of what happens at death becomes genuinely open. The window closes. Does that mean the light on the other side goes out? Penrose has been cautious about the implications for survival after death. He is a physicist, not a mystic, and he knows how quickly such speculations can discredit serious scientific work. But the architecture of permits the speculation in a way that standard neuroscience does not. If consciousness is grounded in the fundamental structure of the universe, if the moments of awareness we experience are the same objective reductions that give reality its definite character, then the self may not be quite the isolated mortal spark we have been told it is. Hameroff has been less cautious. In interviews, he has described death as a loss of quantum information from the brain. Information that, like all quantum information, cannot be destroyed, only dispersed into the universe at large. He has spoken of near-death experiences as moments when the brain approaches the reduction threshold but does not cross it, allowing consciousness to briefly delocalize before returning. These are speculations. But they are speculations that Orkor makes possible, because Orkor treats consciousness as something the brain accesses, not something the brain manufactures. We will return to these implications later. But first, we need to understand the objections, and they are formidable. The most immediate objection is the one I mentioned earlier. The brain is too warm. Quantum coherence is a fragile flower that dies in hot environments. The technical term is decoherence, the process by which quantum superpositions dissolve into classical mixtures through interaction with the environment. Calculations performed in the 1990s, most prominently by physicist Max Tegmark, suggested that any quantum superposition in a microtubule would decohere in about 10 to the 13 seconds, a tenth of a picosecond. Conscious processes take tens or hundreds of milliseconds. The timescales did not match, not by a factor of 10, by a factor of 1 trillion. This was, for many physicists, the end of the story. Orkor was dead on arrival. Quantum coherence in the brain was impossible, and therefore quantum consciousness was impossible. But the story did not end there. In the years since Tegmark's calculation, something unexpected has been discovered. Quantum coherence has been found in biological systems operating at body temperature, not in some exotic theoretical framework, but in experiments, in journals, under conditions that classical physics said were impossible. The first major discovery came from photosynthesis. Plants convert sunlight into chemical energy through a process that begins when a photon strikes a chlorophyll molecule. The energy of that photon must then travel through a network of molecular complexes to reach a reaction center, where it can be captured and stored. Classical physics predicts that this energy transfer should be slow and inefficient. The energy should bounce randomly through the network, losing much of itself to heat along the way. But in 2007, a team led by Graham Fleming at the University of California, Berkeley, discovered something remarkable. The energy transfer was too fast, too efficient. The photon's energy was not bouncing randomly. It was exploring multiple pathways simultaneously, finding the optimal route to the reaction center with an efficiency that only quantum mechanics could explain. The photosynthetic complex was maintaining quantum coherence for hundreds of femtoseconds, far longer than classical estimates predicted possible. And this was happening in a warm, wet, biological environment. The same kind of environment that, according to Tegmark, should destroy coherence in trillionths of a second. Similar results followed. Quantum effects were found in avian navigation. Birds using the Earth's magnetic field to migrate appear to rely on quantum entanglement in cryptochrome proteins in their eyes. Quantum tunneling was identified in enzyme catalysis, proteins accelerating chemical reactions through quantum mechanical processes that classical chemistry could not explain. The new field of quantum biology had been born. None of this proved Orkor, but it removed the strongest objection. If quantum coherence can survive in photosynthetic complexes, why not in microtubules? The hydrophobic pockets Hameroff had pointed to were similar in character to the sites where quantum effects had been found in other biological systems. The theoretical calculations that dismissed quantum coherence in microtubules had assumed that the environment was maximally hostile, but biology, it seemed, had learned to protect quantum states from decoherence. In 2013, Hameroff and his colleagues reported experimental evidence that anesthetics affect microtubule activity. Specifically, they found that the binding of anesthetics to tubulin altered the quantum properties of the protein, dampening the quantum vibrations that Orkor predicted were essential to consciousness. This was indirect evidence, but it pointed in the right direction. In 2022, physicists at Trinity College Dublin, led by Christian Kerskens, published a study in the journal Physics Communications that detected quantum processes in the human brain. Using magnetic resonance imaging techniques sensitive to proton spin dynamics, they found signals that appeared to be mediated by quantum entanglement, correlations between proton spins that could not be explained classically. The researchers were careful. They did not claim to have proven or, but they concluded that quantum coherence in the brain was not only possible but apparently real. The landscape is shifting. What was dismissed as impossible in 2000 is now being treated as an open question in 2024. The experiments are difficult. The signals are faint. The interpretation is contested. But the door that Tegmark thought he had closed is open again. And if Orshaw is right, if consciousness really does arise from quantum processes in microtubules, then every assumption we have made about the relationship between mind and brain will need to be revised. Stop and feel the weight of that for a moment. The materialist consensus, the view that dominates neuroscience, that fills the textbooks, that most educated people absorb without questioning, holds that the brain generates consciousness the way the liver generates bile. It is a secretion, a byproduct, an output of sufficient neural complexity. On this view, the mind is what the brain does. Full stop. There is no mystery beyond the technical details, no hard problem that cannot eventually be dissolved by better imaging techniques and more sophisticated computational models. Consciousness is the whirring of a biological machine, and when the machine stops, the whirring stops. Ork-Owa offers a different picture. The brain is not a generator, but a receiver. Consciousness is not secreted, but accessed. The moments of awareness you experience are not local to your skull. They are events in the quantum fabric of the universe, moments when the gravitational ambiguity of superposed states resolves itself into definite experience. Your brain is the antenna, not the broadcast. This does not mean that the brain is unimportant. An antenna with damaged circuitry picks up nothing but static. A brain with lesions, with degenerative disease, with chemical imbalances will produce disordered consciousness, or no consciousness at all. The dependence of mind on brain, so thoroughly documented by neuroscience, is not contradicted by Ork-Owa. It is reinterpreted. The correlation between brain states and conscious states is explained not by generation but by mediation. The brain is the filter through which universal consciousness becomes localized, individuated, and yours. And this raises the question that no one wants to ask too loudly but everyone secretly wonders about. What happens when the antenna breaks permanently? Penrose and Hameroff have both addressed this question, though with different degrees of caution. Penrose tends to deflect. He's a scientist interested in quantum mechanics and consciousness, not an afterlife theorist. But Hameroff has been more willing to speculate. In interviews, he has described death as the loss of quantum information from the microtubules, information that, according to the laws of physics, cannot be destroyed. Quantum information does not vanish. It disperses. It becomes delocalized into the environment. The patterns that were you, the orchestrated reductions that constituted your moments of awareness, do not disappear. They merge back into the larger fabric. This is not heaven. It is not reincarnation. It is something stranger, a kind of cosmic dissolve, where the individuated consciousness that thought it was, you returns to a substrate it never really left. The question of whether any subjective continuity persists, whether there is still something it is like to be those dispersed patterns, remains unanswerable. But Ork-Owa permits the question. Standard neuroscience does not. We will return to these metaphysical implications in the final part of this exploration. But there is much ground to cover before we reach that point. We need to understand microtubules more deeply, what they are, how they function, what Hameroff claims is happening inside them at the quantum level. We need to examine the mathematics of Penrose's objective reduction, the gravity-induced collapse that forms the theoretical core of Ork-Owa. We need to confront the critics who believe the entire framework is a beautiful but misguided fantasy. And we need to follow the experiments, the laboratory work that is now, finally, beginning to test these claims under controlled conditions. The journey will be long, the subject is difficult, the vocabulary is unfamiliar, but stay with me, this is not idle speculation. This is an attempt by a Nobel Prize winning physicist to answer the hardest question in science. What is consciousness? And the answer he proposes is stranger than almost anyone expected. Before we go further into Ork-Owa itself, we need to spend some time with the structure at its centre, The microtubule is not well known outside cell biology. Most people, if they have heard of it at all, think of it as a kind of cellular skeleton, passive scaffolding that holds the cell's shape. This is not wrong, but it is radically incomplete. Microtubules are among the most remarkable structures in the biological world. They are dynamic, precisely organised, computationally rich, and central to nearly every process that makes a cell a cell. Picture a neuron. The classic image is a cell body with a web of branching tendrils extending from it, dendrites reaching out to receive signals from other neurons, and a long axon stretching away to transmit signals onward. What holds these fragile structures in shape? What guides the traffic of molecules from the cell body out to the distant tip of the axon, a journey that in some neurons can span a metre or more? What partitions the interior of the cell into functional regions? The answer, in each case, is microtubules. A microtubule is a hollow cylinder approximately 25 nanometers in diameter, about 400 times thinner than a human hair. It is composed of a protein called tubulin, which comes in two closely related forms, alpha-tubulin and beta-tubulin. These two forms bind together to create a dimer, a two-part unit that is the building block of the microtubule. Dimers stack end to end to form long chains called protofilaments. 13 protofilaments wrap around each other helically to form the cylindrical wall of the microtubule. The numbers matter: 25 nanometers, 13 protofilaments. These are not random. They reflect deep geometrical constraints. The 13-fold symmetry of the microtubule is found across nearly all eukaryotic organisms, from yeast to humans. Why 13? No one knows for certain. But the number appears to be optimal for stability, flexibility, and the kind of information processing that Hameroff believes occurs within the lattice. Each tubulin dimer can exist in multiple conformational states. The simplest model treats this as a binary switch. The dimer is either in state A or state B, depending on the position of a mobile electron within the protein. These states are not merely structural, they are functional. The conformation of a dimer affects its interactions with neighbouring dimers, with motor proteins that walk along the microtubule surface, with signalling molecules that bind to it. A change in conformation propagates. It influences the states of adjacent dimers. Patterns ripple through the lattice. This is the foundation of Hameroff's proposal that microtubules can compute. Each dimer is a bit. The lattice is a processor. The rules by which neighbouring dimers influence each other constitute a kind of cellular automaton, a computational structure where simple local rules give rise to complex global behaviour. Hameroff has compared microtubule computation to cellular automata, like Conway's game of life, where richly patterned behaviour emerges from the interaction of simple on-off switches following simple neighbour rules. But classical computation is not enough for Orc-Or. Classical computation, no matter how complex, is still algorithmic. It can be simulated on a Turing machine. If microtubules were merely classical cellular automata, they would not solve Penrose's problem. The mind would still be computable. Hameroff's claim is that the computation is quantum. The tubulin dimers do not simply flip between state A and state B. They exist in quantum superpositions of both states simultaneously. The electron whose position determines the conformation is not localized. It is spread out, occupying multiple positions at once, corresponding to multiple conformational states. This superposition is not metaphorical. It is the same kind of superposition that governs the behavior of particles in quantum physics experiments, the same kind that gives rise to interference patterns, entanglement, and all the other strange features of the quantum world. Now scale this up. Imagine not one dimer in superposition, but thousands, millions. Imagine the superpositions of adjacent dimers becoming entangled, correlated in such a way that they must collapse together. Imagine this entanglement spreading through the microtubule lattice, linking dimers across the entire structure. Imagine the same entanglement spreading to other microtubules in the same neuron, and perhaps to microtubules in neighbouring neurons connected through gap junctions that allow direct electrical and possibly quantum communication. What you're imagining is a quantum computer, not built of superconducting circuits at near absolute zero, but built of protein polymers inside living cells at body temperature. A quantum computer whose computational power dwarfs anything classical neurons could achieve. A quantum computer whose outputs are not determined by any algorithm, because the moment of collapse, the moment when superpositions resolve into definite states, is governed by Penrose's objective reduction. a process that Penrose believes is fundamentally non-computable. This is the heart of Orkor. The microtubules perform quantum computation. The computation reaches a threshold. The threshold triggers objective reduction, and that reduction is a moment of conscious experience. Let me put that in perspective. On the standard view of neuroscience, consciousness correlates with neural activity, with patterns of firing across populations of neurons, with the integration of information across brain regions, with the rhythmic oscillations of electrical waves detectable on an EEG. But no one has explained why any of this activity is accompanied by experience. The correlations are documented. The mechanism is missing. Orkor proposes a mechanism. Consciousness is not a correlate of neural activity. Consciousness is a specific physical event, the gravitational collapse of quantum superpositions in microtubules. When this happens, experience occurs. When it does not happen, there is no experience. Just mechanical processing, just input and output, just the zombie behaviour that could in principle be performed by a computer with no inner life at all. The theory is testable. It makes specific predictions about the timing of conscious events, about the effects of disrupting microtubule function, about the signatures of quantum coherence in neural tissue. Some of these predictions have been tested. Others await technology that does not yet exist. But the theory is not, as critics sometimes claim, merely philosophical. It is a physical hypothesis about how the universe works. And if it is right, the implications extend far beyond neuroscience. They reach into the heart of what it means to be alive, what it means to die, and what, if anything, persists when the brain falls silent. The word persists hangs in the air like a question that refuses to dissolve. Because once you have followed the logic of Orkor this far, once you have accepted, even hypothetically, that consciousness arises from quantum events in microtubules, that these events connect the brain to the fundamental fabric of space-time geometry, you are forced to confront something that most neuroscientists carefully avoid. You're forced to ask what happens to consciousness when the brain stops working. On the standard view, the answer is simple and final. Consciousness is a product of brain activity. When brain activity ceases, consciousness ceases. Death is the end of experience, the end of the observer, the end of the story. There is nothing that survives because there was never anything separate from the physical processes of the brain to survive in the first place. The self was always an illusion generated by neurons, and when the neurons fall silent, the illusion stops being generated. This view is clean, parsimonious, and for many people deeply unsatisfying. But dissatisfaction is not a scientific argument. Orkor offers something different. Not immortality in the religious sense, not a soul that floats free of the body, but something far stranger, a possibility that emerges directly from the physics, if the physics is correct. To understand what Orkor implies about death, you need to understand what Penrose believes about the nature of information in quantum systems, and to understand that you need to go back to the mathematics of objective reduction. When a quantum superposition undergoes OR, when it collapses, the information encoded in that superposition does not simply vanish. In Penrose's formulation, the collapse is an event in space-time geometry itself. The superposition represents a kind of separation in space-time, a branching of geometric possibilities. The collapse represents a resolution of that separation, a knitting together of the branches. But here is the key point. The information that was encoded in the superposition is not destroyed. It is, in some sense, written into the fabric of space-time at the moment of collapse. This is a subtle and easily misunderstood claim, so let me try to make it concrete. Imagine you are holding a coin that exists in a quantum superposition of heads and tails. On the standard Copenhagen interpretation of quantum mechanics, the coin has no definite state until you observe it. When you observe it, the superposition collapses, and you see either heads or tails. The other possibility simply disappears. It is as if the universe makes a choice and erases all record of the alternatives. But Penrose's objective reduction suggests something different. The collapse is not merely an epistemological event, not merely a change in what you know about the coin. It is an ontological event, a change in the structure of reality itself. And in that change, the information about the superposition, about what the coin was doing before it collapsed, is not erased. It is incorporated into the geometry of space-time at the fundamental Planck scale level. This sounds abstract, but it has a concrete implication. If quantum information is never truly destroyed, if it is always preserved somewhere in the structure of space-time, then the question of what happens to consciousness at death takes on a different character. Because on the Orchor view, consciousness is precisely this, a sequence of quantum information processing events, each one ending in an objective reduction that writes something into the fabric of reality. Hameroff has been more explicit about these implications than Penrose, who tends toward mathematical caution. In interviews and papers, Hameroff has suggested that the quantum information underlying consciousness might not simply dissipate when the brain dies. It might remain, in some form, encoded in the Planck scale structure of the universe. It might even be accessible, not to instruments, not to any technology we can currently imagine, but to other instances of consciousness that share the same fundamental connection to space-time geometry. This is where Orchor begins to sound less like neuroscience and more like metaphysics, and it is where critics have been most aggressive in their attacks. The suggestion that consciousness might survive death, that some aspect of the self might persist in the geometry of space-time, strikes many scientists as indistinguishable from religious wishful thinking, dressed in quantum vocabulary. But here is where Penrose's Nobel Prize becomes relevant in a way that goes beyond mere credentialing. Penrose has spent his entire career demonstrating that the universe is stranger than our intuitions suggest. His work on black holes showed that singularities, points of infinite density where the laws of physics break down, are not mathematical curiosities but inevitable features of sufficiently massive collapsing stars. His work on the geometry of space-time revealed structures that no one had anticipated. His Penrose tiles showed that non-periodic patterns with perfect local order could tile the plane. Patterns that were later discovered in physical quasi-crystals, earning Dan Shechtman a Nobel Prize. Again and again, Penrose has demonstrated that reality contains possibilities that seem impossible until someone does the mathematics properly. The question is whether Orchor represents another such case, a genuine insight into the structure of reality that will eventually be vindicated, or whether it represents an overreach, a brilliant mind applying its tools to a problem they were not designed to solve. To answer that question, even provisionally, you need to engage with the theory's most controversial claim, the claim that quantum coherence can be maintained in the warm, wet, noisy environment of the living brain. Stop and think about what quantum coherence requires. A quantum system maintains coherence when its quantum states evolve in an orderly way, when the phases of the wave functions that describe the system remain correlated, when superpositions persist without collapsing into definite states. This is what allows quantum computers to perform certain calculations exponentially faster than classical computers. The ability to maintain multiple computational pathways in superposition simultaneously, interfering constructively and destructively to arrive at answers. But coherence is fragile, exquisitely fragile. Any interaction between the quantum system and its environment, any stray photon, any thermal vibration, any electromagnetic fluctuation, can destroy the delicate phase relationships that make quantum computation possible. This process is called decoherence, and it is the great enemy of quantum computing. It is why the most advanced quantum computers in the world operate at temperatures colder than outer space, in vacuum chambers that shield them from every possible environmental disturbance. The human brain is the opposite of these conditions. It operates at 37 degrees Celsius, is saturated with water, is dense with ions and molecules in constant thermal motion. It crackles with electromagnetic activity. By any naive calculation, quantum coherence in the brain should last for about 1 femtosecond, 1/quadrillionth of a second, before being destroyed by decoherence. This is about 1 trillion times shorter than the timescales relevant to neural activity. It is about 1 trillion times shorter than the timescales on which Orchor proposes that quantum computation occurs. This is the objection that physicists raise most frequently against Orchor, and it is a serious objection. It cannot be waved away with appeals to authority or suggestions that critics lack imagination. If quantum coherence cannot survive in the brain long enough to do computational work, then Orch-OR fails regardless of how elegant its mathematics might be. Hameroff and Penrose are aware of this objection. They have addressed it in multiple papers, proposing mechanisms by which microtubules might protect quantum coherence from decoherence far longer than naive estimates suggest. The first mechanism involves the structure of microtubules themselves. The interior of a microtubule is not simply cytoplasm. It is a highly ordered environment, distinct from the chaotic thermal bath of the surrounding cell. The The tubulin proteins that make up the microtubule wall create a cylindrical cage that might shield the interior from environmental noise. More importantly, the specific arrangement of water molecules inside the microtubule is different from bulk water. Water inside microtubules forms ordered structures, sometimes called structured water or exclusion zone water, that have different physical properties from ordinary liquid water. This ordered water might act as a kind of quantum shield. Thermal fluctuations that would destroy coherence in bulk water might be suppressed in the ordered environment of the microtubule interior. The quantum states of tubulin dimers might be protected not in spite of their biological environment, but because of it, because evolution has stumbled upon a molecular architecture that happens to preserve quantum coherence. The second mechanism involves the specific physics of the tubulin protein. The quantum states that Aucor invokes are not the states of entire atoms or molecules, they are the states of individual electrons in the hydrophobic pockets of tubulin. These electrons are shielded from water by the protein's own structure. They sit in tiny nonpolar cavities where the electric field is relatively uniform, where the thermal noise is reduced, where the conditions for quantum coherence are more favourable than anywhere else in the cell. Think of it this way. If you wanted to preserve a delicate quantum state in a hostile environment, you would design a system with multiple layers of protection, an outer shell to block external disturbances, an inner cavity with controlled conditions, and a specific molecular architecture that minimises coupling to thermal modes. Tubulin, Hameroff argues, provides exactly this. Not because it was designed for quantum computation, but because evolution, exploring the space of possible proteins over billions of years, stumbled upon a structure that happens to have these properties. The third mechanism is more speculative and more remarkable. It involves quantum biology, the emerging field that studies quantum effects in living systems. And here, something unexpected has happened. In the decades since Aucor was first proposed, evidence has accumulated that quantum coherence plays a role in biological processes that no one predicted. Consider photosynthesis. When a photon strikes a chlorophyll molecule in a plant cell, it excites an electron. That electron must then travel to a reaction centre where its energy can be harvested for chemical work. The path is not direct. There are many possible routes through the molecular complex. For decades, scientists assumed that the electron took a random walk, bouncing from molecule to molecule until it happened to reach the right destination. This process should be inefficient. Much of the energy should be lost to heat before the electron arrives. But in 2007, a team led by Graham Fleming at the University of California, Berkeley, made a stunning discovery. Using ultrafast laser spectroscopy, they found evidence that the electron does not take a random walk. Instead, it explores multiple pathways simultaneously, in quantum superposition, and interferes constructively to find the most efficient route. The electron behaves like a wave, not a particle, and this wave-like behaviour persists for hundreds of femtoseconds, far longer than anyone thought possible in a warm, wet biological environment. Hundreds of femtoseconds is still very short, but it is orders of magnitude longer than the naive decoherence estimates, and it proves a critical point. The biological world is not automatically classical. Life has found ways to exploit quantum effects at scales and temperatures that physicists assumed were forbidden. Similar quantum effects have been discovered in bird navigation. European robins and other migratory birds navigate using the Earth's magnetic field. But the field is extraordinarily weak. Too weak, it seemed, to interact meaningfully with ordinary chemistry. In the early 2000s, researchers proposed that birds might use a quantum mechanism called the radical pair mechanism. When light strikes certain molecules in the bird's eye, it creates pairs of electrons with entangled spins. The Earth's magnetic field, weak as it is, affects the relative orientation of these spins, which in turn affects the chemistry that follows. The bird's brain reads out the chemical signal and uses it to determine direction. This mechanism requires quantum coherence to persist, long enough for the magnetic field to do its work. Again, far longer than naive estimates suggested possible. And yet the evidence has accumulated that this is exactly what happens. The birds are quantum navigators. Enzyme catalysis provides another example. Enzymes accelerate chemical reactions by factors of 1 million or more. The classical explanation is that enzymes lower the activation energy of reactions by bringing reactants into the correct orientation. But increasingly, Evidence suggests that some enzymes achieve their remarkable speed-ups through quantum tunneling, the process by which particles pass through energy barriers they classically could not surmount. The particles do not go over the barrier, they go through it, exploiting the wave-like nature of quantum mechanics. None of this proves that microtubules perform quantum computation. Photosynthesis, bird navigation, and enzyme catalysis are not consciousness. But they demonstrate something important. Biology and quantum mechanics are not enemies. Life does not simply average away all quantum effects. Life in some cases seems to harness them. In 2014, a team led by Anirban Bandyopadhyay at the National Institute for Materials Science in Japan published results that sent ripples through the ORCOR community. Bandyopadhyay's group studied the electrical properties of microtubulars in isolation, purified tubulin assembled into microtubules in the laboratory, not inside living cells. They found that microtubules conduct electricity in ways that cannot be explained by classical physics alone. The conduction showed signatures of quantum coherent behavior, resonances at specific frequencies, responses that scaled non-linearly in ways characteristic of quantum systems. More striking still, Bandyopadhyay's group found that these effects persisted at room temperature. Not cryogenic temperatures, room temperature. The warm, wet conditions that critics claimed would destroy quantum coherence in femtoseconds. These results are controversial. Other labs have struggled to replicate them. The measurements are technically challenging, and the interpretation is disputed, but the results exist. They are published in peer-reviewed journals. They suggest, at minimum, that the question of quantum coherence in microtubules is not settled. The critics who claim that decoherence definitively rules out ORCOR may be wrong. In 2020, another piece of evidence emerged. A team at the University of California, Santa Barbara, led by physicist Matthew Fisher, proposed that the brain might use quantum entanglement for information processing, but not in microtubules. Fisher's mechanism involves nuclear spins in phosphorus atoms, which are ubiquitous in biological molecules and which have extraordinarily long coherence times because they are so weakly coupled to their environment. Fisher's proposal is distinct from ORCOR, but it shares a crucial premise, that the brain might be a quantum device, that quantum mechanics might play a functional role in cognition, that the naive argument from decoherence might be missing something important. Let me try to convey the stakes of this debate. If ORCOR is wrong, if consciousness is purely classical, if quantum mechanics plays no role in cognition, then the brain is in principle simulable. It may be vastly complex. It may take centuries to fully understand. But there is no fundamental barrier to creating artificial consciousness, no deep mystery beyond our eventual grasp. The hard problem of consciousness is not solved, but it is perhaps solvable by future neuroscience that maps the classical correlates of experience with sufficient precision. If ORCOR is right, if consciousness arises from quantum gravitational objective reduction, then something very different follows. Consciousness becomes tied to the deepest level of physical reality. It becomes non-computable, forever beyond the reach of any algorithm. Artificial intelligence, no matter how sophisticated, remains unconscious unless it somehow replicates the quantum processes of biological neurons. And the nature of death, the question of what happens when the brain ceases to function, becomes genuinely open. This is not a question that science can currently answer. It may not be a question that science can ever answer, at least not through the methods we currently possess. But ORCOR at least puts the question on the table in a way that purely classical neuroscience does not. It suggests that the answer might be surprising. It suggests that materialism, as traditionally conceived, the view that matter in motion is all that exists, that consciousness is nothing but brain activity, that death is simply the cessation of that activity, might be incomplete. Penrose himself is careful about these implications. He does not claim that ORCOR proves the existence of an afterlife or the persistence of the self beyond death. He is a mathematician, and mathematicians are trained to distinguish between what a theory implies and what one might wish it implied. But the theory opens a door. It creates logical space for possibilities that the standard view forecloses. Hameroff has been bolder. In lectures and interviews, he has suggested that the quantum information constituting consciousness might dissipate into the universe at death, not destroyed, but distributed, encoded in the fundamental structure of space-time. If the patient is resuscitated, if the brain restarts, This information might be recollected, reassembled, reinstantiated in the microtubules. If the patient is not resuscitated, the information remains, not localized, not personal in the way we normally think of personhood, but also not obliterated. This suggestion aligns, eerily, with reports from people who have had near-death experiences. The sensation of consciousness existing outside the body, the experience of expanded awareness, of connection to something larger than the self, the feeling, reported again and again across cultures and centuries, that death is not an ending but a transition. These reports prove nothing, of course. They are anecdotes, not data. They can be explained by oxygen deprivation, by the release of endorphins, by the brain's last desperate attempts to make sense of its own dissolution. But they exist. They are remarkably consistent. And if Orkayor is right, they might be pointing towards something real, not supernatural, but natural at a level of nature we do not yet fully understand. Let that settle for a moment. Consider where we are. We have followed Roger Penrose from black holes to consciousness, through non-computability, through Gödel's theorems, through the strange mathematics of quantum gravity. We have followed Stuart Hameroff into the molecular architecture of neurons, into the protein polymers called microtubules, into the quantum states of electrons in hydrophobic pockets. We have encountered a theory that proposes consciousness arises from quantum gravitational events at the Planck scale, events that connect the activity of the brain to the fundamental structure of space-time itself. The theory is speculative. It may be wrong, but it is not empty speculation. It makes predictions. It can be tested, and it addresses directly and unflinchingly the hardest problem in all of science, the problem of explaining how subjective experience arises from objective physical processes. Most scientists who work on consciousness do not accept Orkayor. The mainstream view remains that consciousness is a product of classical neural computation, that quantum mechanics is irrelevant at the scale of neurons, that Penrose and Hameroff have made extraordinary claims without extraordinary evidence. But the mainstream view has its own problem. It has no explanation for consciousness at all. It has correlates, neural patterns that accompany conscious states. It has measurements, brain scans that light up when subjects report experiences, but it has no mechanism. It cannot explain why any of this activity is accompanied by experience rather than proceeding in the dark. This is the hard problem, and the hard problem remains unsolved. It remains unsolved by classical neuroscience. It remains unsolved by cognitive science. It remains unsolved by philosophy of mind. The explanatory gap between objective brain processes and subjective experience is as wide today as it was when David Chalmers named the problem 3 decades ago. Orkayor offers a mechanism. The mechanism may be wrong, but at least it is a mechanism, a specific physical proposal for how experience arises from matter, for how the inner light of consciousness emerges from the darkness of unconscious physics. Now consider what follows if the mechanism is right. If the mechanism is right, consciousness is not an accident. It is not an epiphenomenon, a ghostly byproduct of computation that floats above the physical world without touching it. It is not, as some philosophers have called it, the steam rising from the locomotive of the brain. Consciousness, in the framework of Orkayor, is fundamental. It is woven into the fabric of reality at the deepest level physics can reach. It is not generated by matter. It is what matter does when matter encounters itself at the threshold between quantum possibility and classical actuality. This is a profound shift. It repositions consciousness from the periphery of physics to its centre, and it raises questions that go far beyond the scope of neuroscience, far beyond the operating theatre, far beyond the anesthesiologist's careful calibrations. Questions about what consciousness is, where it resides, and whether it can exist in forms radically different from the one we know. Consider the first question. What is consciousness? In the standard view, consciousness is information processing of a particular kind. It is the brain representing itself to itself, modelling its own states, generating an internal narrative that we experience as the stream of thought. This view has a certain elegance. It explains consciousness as a kind of software, a pattern of activity that could, in principle, be instantiated in any sufficiently complex substrate. Upload the pattern to a computer, and the computer would be conscious. Copy the pattern, and you would have 2 consciousnesses. Delete the pattern, and consciousness would simply cease. Orkayor rejects this view. Consciousness, in the Penrose-Hameroff framework, is not software. It cannot be abstracted from its physical substrate. It arises specifically from quantum gravitational events in microtubules, events that depend on the precise molecular structure of tubulin proteins, on the quantum coherence sustained by aromatic ring electrons, on the interface between the biological and the physical, at scales we're only beginning to understand. This means consciousness cannot be uploaded. It cannot be copied. It cannot be simulated by a classical computer, no matter how powerful. The mind is not a program. It is a process that unfolds in a specific physical substrate according to laws that include, crucially, the mysterious dynamics of quantum state reduction. Some will find this conclusion limiting. The dream of digital immortality, of uploading one's consciousness to the cloud, of living forever as a pattern of information, this dream evaporates if or is true. Consciousness is not separable from the particular physical processes that give rise to it. Destroy the microtubules, and you destroy the consciousness they sustain. There is no backup, there is no copy. There is only the original, embedded in flesh, embedded in protein, embedded in the quantum fabric of biology. But others will find this conclusion strangely comforting. It means you're not replaceable. It means your consciousness is not a generic computation that could be running anywhere, on any substrate, in any possible world. It means there is something irreducibly specific about being you, something tied to the particular arrangement of molecules in your particular brain, something that could not exist in any other form. You're not fungible, you're not duplicable, you are in a deep physical sense unique. Now consider the second question. Where does consciousness reside? In the standard view, consciousness is localized in the brain. Specifically, it is localized in the neural networks that process information, perhaps concentrated in the cerebral cortex, perhaps distributed across multiple regions, but always contained within the bone vault of the skull. The brain is the organ of consciousness. Damage the brain, and consciousness is altered. Destroy the brain, and consciousness ends. Orkor complicates this picture. Consciousness in the Penrose-Hameroff framework arises from quantum gravitational events that connect the activity of microtubules to the fundamental structure of space-time. The Planck scale is not localized in any particular place. It is everywhere. It is the substrate beneath all space, the granular foundation on which the continuous geometry of general relativity is built. When a quantum superposition in a microtubule reaches the objective reduction threshold, when the self-collapse occurs, this event is not happening only in the brain. It is happening in space-time itself. The brain is the locus of the biological process, the site where microtubules sustain coherent quantum states, the organ that orchestrates the reductions. But the reductions themselves, the moments of objective reduction that Penrose identifies with conscious experience, occur at a level of reality that is deeper than any particular spatial location. This is subtle. It does not mean that consciousness is floating free, disembodied, distributed across the universe. The brain remains necessary. The microtubules remain necessary. The specific biological structures that sustain quantum coherence are the conditions for consciousness to arise. But consciousness, once it arises, is connected to something that is not bounded by the brain. It touches the Planck scale. It participates in the fundamental physics of the universe. Hameroff has put this more directly. The brain, he suggests, is not a generator of consciousness. It is a receiver. It is an antenna that tunes into something deeper, something that exists at the level of space-time geometry, something that the microtubules access and orchestrate into the specific experiences we call our minds. Stop and feel the weight of that metaphor. A radio does not create the music it plays. The music exists as electromagnetic waves, propagating through space, encoded in frequencies that the radio circuits are designed to detect. The radio receives the signal, amplifies it, converts it to sound waves that the ear can hear. If you smash the radio, the music stops, but only because the radio is no longer receiving. The music is still out there. The signal continues to propagate. Is the brain like a radio? Is consciousness a signal that the brain receives rather than generates? This is the question that Orkor opens, even if Penrose and Hameroff would phrase it more carefully, with more caveats, with more attention to the distinction between metaphor and mechanism. The metaphor has limits. There is no external broadcaster in the Orkor framework. Consciousness is not being transmitted from somewhere else. The quantum gravitational events that constitute conscious moments are happening in the microtubules, not arriving from outside them. But there is something to the metaphor nevertheless. The microtubules are accessing a level of reality, the Planck scale, the proto-conscious information embedded in space-time geometry, that is not itself created by the brain. The brain orchestrates, it tunes, it shapes. But the fundamental ingredient, the raw material from which experience is made, exists independently of any particular brain. This has implications. It suggests that consciousness is not an evolutionary accident, not a lucky byproduct of nervous systems that happen to become complex enough. It suggests that consciousness is inherent in the universe, latent in the structure of space-time, waiting to be accessed by any physical system capable of sustaining the right kind of quantum processes. This is close to what philosophers call panpsychism, the view that consciousness is a fundamental feature of reality, present in some form in all matter. But Orkor is not classical panpsychism. It does not say that rocks are conscious, that electrons have experiences, that every particle in the universe feels something. It says that consciousness arises when specific quantum gravitational events occur under specific conditions. Most matter does not sustain these events. Most matter is unconscious, but the potential for consciousness is built into the physics of the universe. It is not added later, not emergent from complexity, not a trick of evolution. It is fundamental. Penrose has used a different term, proto-consciousness. The Planck scale, the fundamental geometry of space-time, contains something like information, not conscious in itself, but capable of becoming conscious when orchestrated by the right biological structures. The microtubules are the instruments that transform proto-consciousness into actual consciousness, that convert the latent into the manifest, that turn the background hum of quantum geometry into the symphony of subjective experience. Now consider the third question, the one that haunts the operating theatre, the one that troubles every person who has ever watched a loved one slip away. Can consciousness exist in forms radically different from the one we know? If consciousness is information processing, then in principle, it can exist in any substrate that processes information in the right way. Computers, robots, alien beings with silicon neurons, disembodied minds running on vast networks of fibre optic cables. All of these are possible conscious beings waiting to be built or discovered. If consciousness requires microtubules, if it requires the specific quantum gravitational events that occur in tubulin proteins under conditions of orchestrated coherence, then the possibilities narrow. Consciousness requires biology, or at least it requires something functionally equivalent to biology, some physical system capable of sustaining quantum coherence at the relevant scales, capable of undergoing objective reduction at the Penrose threshold, capable of participating in the fundamental physics that connects mind to space-time. We do not know what such a system would look like. We do not know whether alien biology, evolved on a different planet under different conditions, would produce microtubules or something analogous. We do not know whether artificial systems could ever replicate the quantum dynamics of neurons. We do not know whether consciousness is cosmically rare, confined to the particular molecular machinery that evolution produced on Earth, or cosmically common, arising wherever the conditions for quantum biological processes happen to be met. But we can say one thing with confidence. If Orkor is true, the question of artificial consciousness becomes much harder. A classical computer cannot be conscious, no matter how sophisticated its programming, no matter how convincingly it simulates human conversation, no matter how many tasks it performs that seem to require understanding. Classical computers do not undergo quantum state reduction. They do not access the Planck scale. They process information, but the processing is not accompanied by experience. The lights are on, but nobody is home. This claim is controversial. Many researchers in artificial intelligence dismiss it as romantic mysticism, as a desperate attempt to preserve human specialness in the face of machines that are rapidly surpassing human capabilities. If a machine behaves as if it is conscious, the argument goes, then for all practical purposes, it is conscious. Behaviour is the only evidence we have. We cannot peer into another being's subjective experience. We can only observe what it does, what it says, how it responds. A sufficiently sophisticated machine would pass every test we could devise. Why should we deny it consciousness? Penrose's answer comes from Gödel, a machine that operates by fixed algorithms, no matter how complex, no matter how adaptive, no matter how good at mimicking human behavior, is bounded by the theorems of incompleteness. There are truths it cannot reach. There are insights it cannot have. Human mathematicians can see these truths, can step outside the system, can recognize the Gödel sentence that the system cannot prove. This capacity, Penrose argues, cannot be algorithmic. It must arise from something else, from the non-computable quantum gravitational processes that consciousness taps into. The debate is unresolved. It may remain unresolved for decades. But the stakes are clear. If Penrose and Hameroff are right, the dream of conscious machines is not just technically difficult, it is physically impossible within the current computational paradigm. A different kind of technology would be needed, a quantum gravitational technology, a technology that replicates the physics of microtubules, a technology that we do not currently know how to build and may never know how to build. The mind, in this framework, is not reducible to algorithms. It is not a pattern that can be copied to silicon. It is a physical process of a very specific kind, rooted in the deepest structures of reality, irreplaceable and irreducible. Let me try once more to give you a feel for what is at stake. You're lying awake at 3 a.m. The house is quiet. The city outside your window is quiet. Your thoughts drift. You think about people you have lost. You think about people you will lose. You think about the moment, inevitable but unimaginable, when you yourself will cease to think. The standard view offers you a grim but clean consolation. Consciousness is brain activity. When the brain stops, consciousness stops. There is nothing to fear because there will be nothing. No suffering, no regret, no awareness of absence. The light goes out, and there is no one left to notice the darkness. But the standard view also offers you nothing else. No possibility of anything beyond the final electrical silence. No mechanism by which any part of you could persist. No connection between your mind and anything larger than the 3 pounds of tissue inside your skull. Or offers something different. It does not promise immortality. It does not promise heaven or reincarnation or any of the religious consolations that humans have invented across the millennia. It is not theology dressed in physics, but it opens a door that the standard view keeps firmly closed. If consciousness arises from quantum gravitational events at the Planck scale, then consciousness is not confined to the brain in the way we normally assume. The brain is the site of the orchestration, the biological structure that sustains the quantum coherence, the instrument through which proto-conscious information becomes actual experience. But the information itself, the quantum states, the superpositions, the correlations that constitute the substrate of mind, exists at a level of reality that is deeper than neurons, deeper than cells, deeper than the distinction between life and death. When the brain stops, the orchestration stops. The coherent quantum states in the microtubules decohere. The superpositions collapse. The biological conditions for consciousness are no longer met. But what happens to the information? In classical physics, information is lost when structures are destroyed. Burn a book, and the information in the book is gone, irretrievably scrambled, dispersed into heat and ash. But quantum mechanics is different. Quantum information is never truly destroyed. It is conserved, redistributed, encoded in the correlations between particles that once interacted. This is one of the deepest principles of quantum theory: unitarity, the conservation of information, the impossibility of truly erasing what has existed. If the quantum states in microtubules carry information about conscious experience, what happens to that information when the microtubules cease to function? Hameroff's suggestion, speculative, tentative, impossible to prove with current technology, is that the information dissipates into the universe, encoded in the geometry of space-time, preserved in a form that is no longer localized, no longer personal, but also not obliterated. This is not survival in any conventional sense. It is not a soul floating to heaven. It is not reincarnation in a new body. It is something stranger. The possibility that the information constituting your conscious experience becomes part of the fundamental structure of the universe, woven into the Planck scale geometry that underlies all of space and time. And if the brain restarts, if the heart is restarted, if the microtubules regain their coherence, if the conditions for orchestrated objective reduction are restored, then perhaps, just perhaps, some of that information could be recollected, reassembled, reinstantiated. This would explain something that has puzzled researchers studying near-death experiences for decades. When patients are revived after cardiac arrest, after minutes without heartbeat, without blood flow to the brain, without any measurable neural activity, and some of them report experiences, vivid experiences, coherent experiences, experiences that seem impossible if consciousness requires an active brain. They report floating above their bodies, watching the resuscitation efforts from the ceiling. They report moving through tunnels toward light. They report encounters with deceased relatives, with beings of radiance, with presences that communicate without words. They report feelings of peace, of love, of connection to something infinitely larger than themselves. These reports are remarkably consistent across cultures, across centuries, across religious traditions. People who have never heard of near-death experiences describe the same elements when they are revived. People who are atheists, who have no expectation of an afterlife, report the same phenomena as devout believers. Something is happening. Something that the standard model of consciousness cannot explain. Skeptics offer explanations. Oxygen deprivation causes hallucinations. The dying brain releases a flood of endorphins. The temporal lobe, deprived of normal input, generates the illusion of movement through space. The expectation of death triggers memories and fantasies that feel real in the moment. These explanations are not unreasonable, but they do not fully account for the data. Some patients report accurate perceptions of events that occurred while they were clinically dead, details they could not have seen or heard if their consciousness were confined to a non-functioning brain. Some patients report experiences during periods when EEG shows no measurable electrical activity in the cortex. OR does not prove that these experiences are real. It does not prove that consciousness persists after death, but it provides a framework in which such persistence becomes physically conceivable. If consciousness is not generated by the brain but mediated through it, if the brain is an antenna tuned to proto-conscious information at the Planck scale, then the failure of the antenna does not necessarily mean the signal has ceased. It might mean only that the signal is no longer being received. The antenna metaphor again, the radio smashed, the music continuing. We are at the edge of what science can tell us. Beyond this point lies speculation, philosophy, faith. Penrose has been careful not to make claims that outrun the evidence. Hameroff has been bolder, more willing to explore the implications, more willing to connect OR to the perennial questions about death and meaning that humans have always asked. But both of them have done something remarkable. They have created a scientific theory that addresses consciousness directly, a theory that makes predictions, a theory that can be tested, a theory that, if confirmed, would revolutionize our understanding of what we are and what we might become. The evidence is accumulating. The quantum coherence in microtubules that seemed impossible has been observed. The anesthetic binding sites that the theory predicted have been found. The timescales of neural processes are coming into alignment with the timescales of orchestrated objective reduction. None of this proves that OR is true. Science does not work by proof. It works by converging evidence, by predictions confirmed, by competing theories compared, and the ones that fail discarded. OR is still competing. It is still being tested. It may still be wrong, but it has survived longer than its critics expected. It has grown stronger as the objections have been addressed, and it continues to offer something that no other theory of consciousness provides, a bridge between the objective world of physics and the subjective world of experience, a mechanism for how matter becomes mind, an answer to the hardest problem in all of science. The operating theatre is quiet now. The surgery is finished. The patient is being wheeled to recovery. In a few hours she will wake. She will open her eyes and see the world again. The fluorescent lights, the faces of nurses, the ordinary details of a hospital room. She will not remember the hours she spent unconscious. For her, that time did not exist. It was a gap, a void, a period when her subjective experience simply stopped. But something was happening in that void. In the microtubules of her neurons, quantum coherence was being maintained, was being modulated, was being suppressed by the anesthetic that kept her under. The delicate balance between quantum and classical, between superposition and collapse, was being shifted, just enough to prevent the orchestrated reductions that constitute conscious moments. She was not dead. Her brain was active, processing information, maintaining vital functions. But she was not conscious. The conditions for OR were not met. The threshold was not reached. The quantum gravitational events that Penrose identified with conscious experience did not occur, and now, as the anaesthetic wears off, as the propofol clears from her system, the balance shifts back. The microtubules resume their quantum dance, the superpositions build, the threshold approaches. And at some moment, a moment she will not remember, a moment that marks the boundary between absence and presence, an objective reduction occurs. The light comes on. She opens her eyes. But what is it like to be that light? What is it like to be the moment itself? Not the moment observed, not the moment remembered, but the moment as it happens, from the inside. This is the question that haunts philosophy. This is the question that science has spent centuries avoiding. And this is the question that orchestrated objective reduction, alone among physical theories, attempts to answer. The philosopher Thomas Nagel asked it most famously in 1974, in a paper that has shaped consciousness studies ever since. What is it like to be a bat? The question seemed simple. Bats experience the world through echolocation, through sound waves bouncing off surfaces and returning to their ears in patterns that create a kind of sonic map of their environment. We can study the physics of echolocation. We can measure the frequencies, the timings, the neural pathways that process the returning signals. We can describe, in exquisite detail, how a bat's brain represents the world. But none of this tells us what it is like to be a bat. None of this captures the subjective quality of bat experience, the way the world feels from inside bat consciousness, the texture of sonic perception, the shape of bat awareness. There is something it is like to be a bat. Nagel was certain of that. Bats are conscious creatures. They have experiences, but we cannot know what those experiences are like, because we are not bats. We are trapped inside our own consciousness, able to report on our own experiences but unable to truly access the experiences of any other being. This is the hard problem in its purest form. Not how does the brain process information? We can study that. Not how do organisms respond to their environment? We can measure that. But how does any physical process, any arrangement of matter, any pattern of neural firing give rise to subjective experience? How does third-person description of brain activity translate into first-person experience of being alive? David Chalmers, who coined the phrase hard problem of consciousness in 1995, has argued that this problem may be fundamentally unsolvable within the standard materialist framework. We can explain everything about the brain, every neuron, every synapse, every chemical gradient, every electrical pattern, and still be left with the question of why there is experience at all. Why isn't the brain just processing information in the dark? Why isn't there nothing it is like to be you? The standard answer, the answer that most neuroscientists give when pressed, is that consciousness is simply what information processing feels like when it reaches a certain level of complexity. Consciousness is an emergent property, like the wetness of water emerging from hydrogen and oxygen atoms, like the flight of a bird emerging from feathers and hollow bones and muscle contractions. You cannot find wetness in a single water molecule, you cannot find flight in a single feather, and you cannot find consciousness in a single neuron, but put enough neurons together, connect them in the right way, and consciousness emerges. This answer has a certain appeal. It fits our intuitions about complexity. It avoids the need for any new physics. It keeps consciousness firmly within the materialist worldview that has served science so well. But the appeal is hollow, because emergence, as standardly understood, does not actually solve the hard problem. It postpones it, it rebrands it, it gives it a new name and then moves on. When we say that wetness emerges from water molecules, we mean something quite specific. Wetness is a macroscopic description of molecular behaviour. It refers to the way molecules interact with surfaces, with each other, with our skin. There is no mystery in wetness. Given the physics of molecular interaction, wetness is predictable, explicable, reducible. If we knew everything about water molecules and their interactions, we could derive wetness from first principles. But can we derive experience from first principles? Can we deduce, from any description of neural activity, no matter how complete, what it is like to see the colour red, what it is like to feel grief, what it is like to understand a mathematical proof? The answer, Chalmers argues, is no. There is an explanatory gap between physical description and conscious experience. The gap is not a gap in our current knowledge, a gap that more neuroscience will eventually close. It is a gap in principle. The concepts we use to describe physical processes, mass, charge, spin, information, are not the right concepts for capturing subjective experience. Experience is a different kind of thing. It requires its own vocabulary, its own categories, its own place in the ontology of the universe. This is where Penrose and Hameroff enter the conversation, not to solve the hard problem in the sense of eliminating it, but to take it seriously as a fundamental feature of reality. The standard approaches to consciousness treat experience as derivative, as secondary, as something that emerges from matter when the matter gets complicated enough. Penrose's approach is different. He treats experience, or rather proto-consciousness, as fundamental, as basic to the fabric of reality as space and time, as woven into the geometry of the universe at the Planck scale. This is a radical move. It means that consciousness is not a late addition to the cosmos, not a biological accident, not an emergent property of sufficiently complex computation. Consciousness, in some primitive form, is there from the beginning. It is part of what the universe is. But what does primitive form mean? What is proto-consciousness? How can something be conscious without being conscious in the way we are conscious? Here Penrose draws on the work of another philosopher, Alfred North Whitehead, the process philosopher who argued that experience is the fundamental category of reality, that even the simplest physical events have an experiential aspect, a prehension of their environment, a way of being that is more than mere mechanism. Whitehead's philosophy is dense, difficult, often obscure, but his central insight is clear. We should not start with dead matter and try to explain how it becomes alive, how it becomes conscious. We should start with experience and try to explain how it becomes complex, how it becomes differentiated, how it becomes the rich inner life of human beings. Penrose is not a Whiteheadian. He is a physicist and mathematician, and his vocabulary is different. But his framework shares something with Whitehead's vision. The objective reductions that occur at the Planck scale, the moments when quantum superpositions collapse due to gravitational effects, are not mere physical events. They carry proto-conscious information. They are the universe making tiny decisions, selecting one possibility out of many. And this selection is not random, not arbitrary. It is influenced by the mathematical structure of reality, by what Penrose calls the Platonic realm, the domain of mathematical truths that exists independently of physical instantiation. Let that phrase settle for a moment. The Platonic realm. Mathematical truths existing independently of physical instantiation. Penrose believes, and this is another point where he departs from mainstream physics, that mathematical objects are real. Not real in the sense that chairs and tables are real, not real in the sense of occupying space and time, but real in the sense of having an existence that does not depend on human minds, human languages, human civilizations. The number 17 was true before there were humans to count. The irrationality of the square root of 2 was a fact before any mathematician proved it. The structure of the Mandelbrot set was waiting to be discovered, not invented. This is Platonism in its pure form, and most physicists, if they thought about it, would probably agree. The laws of physics seem to be mathematical. The universe seems to be describable in equations. The unreasonable effectiveness of mathematics in the natural sciences, as Eugene Wigner famously called it, suggests that mathematics and physics are not separate domains, but deeply intertwined aspects of a single reality. But Penrose takes this further. He suggests that consciousness, human consciousness, the consciousness that allows us to understand mathematics, to grasp proofs, to see why the square root of 2 must be irrational, is itself connected to this Platonic realm. We are not just computing machines that happen to manipulate symbols. We are beings who can access mathematical truth directly, through understanding, through insight, through what Penrose calls non-computational mental processes. And here is where everything connects. If consciousness can access the Platonic realm, if understanding involves more than computation, more than symbol manipulation, more than information processing, then consciousness must involve something non-computational. It must involve something that transcends the algorithmic. And the only place in known physics where non-computability appears is in quantum mechanics, in the collapse of the wave function, in the measurement problem that has troubled physicists since the 1920s. The objective reductions that Penrose proposes as the basis of Orc-Core are non-computational events. They are moments when the universe selects an outcome that cannot be predicted, even in principle, by any algorithm. They are moments of genuine indeterminacy, genuine choice, genuine novelty. And if these moments carry proto-conscious information, if they are the universe experiencing itself at the smaller scale, then human consciousness, mediated through microtubules, is a concentration, an amplification, a flowering of something that is already present in the fabric of reality. The hard problem does not disappear in this framework, but it is transformed. We no longer have to explain how dead matter suddenly becomes conscious. We have to explain how primitive proto-conscious events become orchestrated into the complex unified experience of being human. This is still a hard problem, but it is a different kind of hard problem. It is a problem of organization, of integration, of amplification, not a problem of creation ex nihilo. Stop and feel the weight of this shift. For 300 years, since Descartes split the world into mind and matter, Western philosophy has struggled with the question of how the two relate. How does the ghost get into the machine? How does the soul attach to the body? How does subjective experience arise from objective physics? The answers have been unsatisfying. Dualism, the view that mind and matter are fundamentally different substances, faces the problem of interaction. If mind is not physical, how does it affect the physical brain? How does a thought cause a hand to move? Materialism, the view that everything is physical, including mind, faces the hard problem. If mind is just matter in motion, why is there experience at all? Why doesn't the brain process information unconsciously, without any inner light? Penrose and Hameroff offer a third way. They do not eliminate either mind or matter. They do not reduce one to the other. Instead, they propose that both are aspects of a deeper reality, a reality in which proto-consciousness is fundamental, in which the Platonic realm of mathematical truth is woven into the fabric of space-time, in which objective reductions at the Planck scale are the elementary events from which all experience is built. This is not a solution in the sense of making the mystery disappear. It is a reframing of the mystery, a relocation of the hard problem from the biological level to the cosmological level, but such reframings can be progress. The mystery of how biological organisms reproduce was once considered fundamental, irreducible, perhaps requiring a vital force beyond physics. Now we understand reproduction in terms of DNA, proteins, cellular mechanisms. The mystery has not disappeared. We still do not fully understand the origin of life, but it has been transformed into a different kind of question, a question about chemistry and information rather than about a mysterious vital force. Perhaps consciousness will follow the same path. Perhaps Orkor, or some successor theory that builds on its insights, will transform the hard problem into a different kind of question, a question about how proto-conscious events combine, about how quantum coherence is maintained in biological systems, about how the mathematics of objective reduction relates to the phenomenology of experience. These would still be hard questions, but they would be scientific questions, questions that could be investigated experimentally, questions that might eventually yield to human understanding, or perhaps not. Perhaps consciousness will forever remain mysterious, forever beyond the reach of scientific explanation, forever the one thing in the universe that cannot be captured in equations and theories. This possibility cannot be ruled out. The hard problem may truly be hard, not just difficult, but impossible. But Penrose does not believe this. He believes that consciousness is comprehensible, that it can be understood, that it is part of the natural order and therefore subject to natural explanation. He also believes that the explanation will require new physics, physics that we do not yet have, physics that will emerge from a successful quantum theory of gravity. Orkor is a promissory note, a placeholder, a sketch of what the full theory might look like. But it is more than speculation. It is a framework that makes predictions, that connects to known physics, that can be tested against evidence. And it is a framework that takes consciousness seriously as a feature of the universe, not an illusion, not an epiphenomenon, not an emergent gloss on underlying mechanism, but a real aspect of reality that any complete physics must account for. This brings us back to the operating room, back to the patient opening her eyes, back to the moment when the light comes on. What happened in that moment? What is an objective reduction? Not the physics of it, not the mathematics, but the experience. Penrose's answer is that the experience is precisely what differentiates objective reduction from other physical processes. An objective reduction is not just a state change. It is not just a transition from quantum superposition to classical definiteness. It is a selection, a decision, a moment when the universe chooses, and in choosing, experiences. The language is strange. It sounds almost mystical, but Penrose insists it is not mystical. It is physics. The experience associated with objective reduction is not added on from outside, not imposed by some external observer, not dependent on interpretation. It is intrinsic to the event itself. It is what makes an objective reduction different from a random quantum fluctuation or a measurement-induced collapse. It is the missing ingredient in quantum mechanics, the ingredient that explains why there is a definite outcome, why the universe has a single history, why observation matters. The word for this intrinsic experiential aspect is qualia, the what it is like of conscious experience, the redness of red, the pain of pain, the taste of coffee. These are the hard data of consciousness, the phenomena that any theory must explain. And Penrose's framework suggests that qualia are not emergent properties of complex computation. They are fundamental features of reality, present in every objective reduction, concentrated and amplified in the orchestrated reductions that occur in biological systems. If this is true, and we must keep returning to that conditional, then consciousness is not a late addition to the universe. It is not an evolutionary accident. It is not a human peculiarity. Consciousness in some form is everywhere. It is in every atom, every photon, every quantum of gravitational energy. Not the rich unified consciousness of human experience that requires the special conditions of biological microtubules, but proto-consciousness, the building blocks of experience, the raw material from which minds are made. This is panpsychism, the view that consciousness is a fundamental feature of matter. It is an ancient view, held by philosophers from Spinoza to Leibniz to William James. It has been marginalized in modern philosophy, dismissed as mystical or unscientific, rejected as incompatible with the materialist worldview that has dominated science since the Enlightenment. But panpsychism is making a comeback. Philosophers like David Chalmers, Galen Strawson and Philip Goff have argued that panpsychism may be the only way to solve the hard problem. If consciousness does not emerge from non-conscious matter, then consciousness must be present in matter from the start. This does not mean that electrons are conscious in the way we are conscious. It means that electrons have some minimal experiential aspect, some primitive form of what it is like to be an electron. This aspect is too simple to count as experience in any rich sense, but it is the seed from which richer experiences grow. Penrose and Hamerof's contribution is to provide a physical mechanism for panpsychism. They do not just assert that consciousness is fundamental. They explain how fundamental proto-consciousness becomes complex biological consciousness. The mechanism is objective reduction orchestrated by microtubules. The Planck scale proto-conscious events are channeled, organized, amplified by the quantum processing in neuronal cytoskeletons. The result is what we experience: the stream of consciousness, the inner light, the feeling of being alive. But there is a puzzle lurking in this framework, a puzzle that philosophers call the combination problem. If proto-conscious events are everywhere, if every objective reduction carries some minimal experiential aspect, why don't we experience the whole universe? Why is consciousness bounded, located, individual? Why am I me and not you? Why is there a difference between my consciousness and the chair's consciousness? Assuming the chair has any consciousness at all, the combination problem is serious. It has led many philosophers to reject panpsychism, to argue that distributing consciousness throughout matter just multiplies the mystery rather than solving it. If atoms are proto-conscious, how do they combine to form a single unified consciousness? How do billions of neurons, each presumably hosting its own micro-experiences, come together to produce the unified experience of a single mind? Hamerof's answer involves the quantum properties of microtubules. Quantum coherence, he argues, is precisely the mechanism of combination. When microtubules across different neurons become entangled, when their quantum states correlate, the proto-conscious aspects of their objective reductions become unified. The boundaries of consciousness are not anatomical. Not the boundaries of neurons or brain regions, but quantum mechanical. Consciousness extends as far as quantum coherence extends, and the unity of consciousness at any moment corresponds to the extent of entanglement in the brain's microtubule network. This is elegant. It provides a physical correlate of the unity of consciousness. It explains why anesthetics, which disrupt quantum coherence, also disrupt conscious experience. It explains why meditation and focused attention, which may enhance coherence, are associated with altered states of consciousness. It explains why brain damage can fragment consciousness, can produce split brain phenomena, can divide what was once unified, because such damage destroys the coherence conditions required for combination. But it remains controversial. The same physicists who question whether quantum coherence can survive in the warm, wet brain also question whether quantum coherence can explain the unity of consciousness. The timescales seem wrong, the spatial scales seem wrong. The whole idea of macroscopic quantum effects in biological tissue seems, to many experts, wishful thinking dressed in scientific language. The debate continues. Experiments are proposed, conducted, analysed, disputed. New evidence emerges. Old objections are revived. The scientific community, or rather the small fraction of the scientific community that takes Auchor seriously enough to engage with it, remains divided. And through it all, the hard problem remains. Even if Auchor is correct in every detail, even if quantum coherence in microtubules is demonstrated, even if objective reductions are observed at the predicted timescales, even if the anesthetic binding sites confirm the theory's predictions, we will still face the question of why. Why do objective reductions carry experiential aspects? Why is there something it is like to be a quantum system in gravitational superposition? Why does the mathematics of space-time geometry translate into the feeling of being conscious? Penrose is honest about this. He does not claim to have solved the hard problem. He claims only to have relocated it, to have moved the mystery from biology to physics, from neurons to Planck-scale events, from emergence to fundamental law. The mystery remains. But it is now a mystery about the basic structure of reality, not a mystery about how complexity produces novelty. And mysteries about basic structure are perhaps more tolerable. We accept that charge is fundamental, that mass is fundamental, that space-time is fundamental. Perhaps we must accept that proto-consciousness is fundamental too. The patient is in recovery now. The fluorescent lights hum overhead. A nurse checks her vital signs, notes them on a chart, moves on to the next bed. The ordinary rhythms of a hospital continue. The squeak of shoes on linoleum, the distant beep of monitors, the murmur of voices in the hallway, and inside her skull, invisible to any instrument, something extraordinary is happening. Microtubules are vibrating at terahertz frequencies. Quantum superpositions are building, spreading, approaching thresholds. Objective reductions are occurring, 40 times per second according to Auchor, each one a moment of conscious experience, each one a window onto the Planck-scale geometry of space-time. She does not know this. She knows only that she is waking up, that her throat is sore, that she is thirsty, that the surgery is over and she is still alive. These are the facts of her experience. The physics underlying that experience is invisible to her, as invisible as it has been to every conscious being who ever lived. But the physics is there. Or so Penrose and Hameroff believe. The orchestra is playing, even if no one can see the musicians. The reductions are occurring, even if no instrument can detect them. And consciousness, her consciousness, your consciousness, all consciousness, is flowing from the deepest level of physical reality, from the place where space-time geometry meets quantum mechanics, from the foundation of the universe itself. The window in the recovery room is dark now. Night has fallen while she was unconscious. The city lights are visible in the distance, millions of them, each one marking a place where other conscious beings live, work, love, suffer. Each of those beings carries the same mystery. Each of those beings is a concentration of Planck-scale proto-consciousness, organized by evolution, maintained by the quantum coherence of microtubules, experiencing the world from inside a 3-pound organ that still does not fully understand itself. The nurse dims the lights, the patient closes her eyes, and the orchestra plays on. But now we must turn to the implication that Penrose himself approaches most carefully, the one that Hameroff has been more willing to discuss openly. the one that transforms Orshaw from a theory of consciousness into something that touches every human life at its most vulnerable moment. The implication concerns what happens when the orchestra stops playing, what happens when the brain ceases to function, what happens when the patient in the recovery room decades from now does not wake up. Death. The word itself carries weight that no scientific theory can fully address. It is the horizon beyond which all human plans terminate, the boundary that gives shape to every life by marking where that life will end. Philosophers have wrestled with it since philosophy began. Religions have organized themselves around it. Medicine defines itself partly by its opposition to it. And consciousness studies, whether practitioners admit it or not, cannot escape its shadow. Because the question of what consciousness is cannot be separated from the question of what happens to consciousness when the body fails. For most of modern neuroscience, the answer has seemed straightforward. Consciousness is what the brain does. When the brain stops doing what it does, consciousness ends. There is no more mystery to it than asking what happens to the flame when you blow out a candle. The flame does not go anywhere. The flame simply ceases to exist. The conditions that supported it no longer obtain. The process that constituted it no longer occurs. End of story. This view has a name among philosophers. It is called the termination thesis. Consciousness begins when the brain begins generating it, continues as long as the brain continues generating it, and terminates when the brain stops. The termination thesis follows naturally from the production model of consciousness, the idea that the brain produces experience the way the liver produces bile, the way the heart produces circulation, the way the lungs produce respiration. Organs produce their products. When the organ fails, the product ceases. Simple, clean, materialist, consistent with everything we know about how biological systems work. But Orshaw, if it is correct, suggests a different relationship between brain and consciousness. Not production, but mediation. Not generation, but reception. Not creation, but selection. And this different relationship opens a door that the termination thesis keeps firmly closed. Let me be careful here. Penrose is a physicist. His training, his temperament, his entire career has been built on rigour, on mathematics, on testable predictions, on the patient accumulation of evidence. He does not make claims he cannot support. He does not speculate wildly about matters beyond the reach of science. And when the conversation turns to death and what follows it, he becomes notably cautious. He will discuss the physics. He will discuss the mathematics. He will discuss the implications of his theory for the nature of consciousness. But he will not make grand pronouncements about immortality or the afterlife or the fate of the soul. That territory lies beyond physics, and Penrose knows where his expertise ends. Hameroff, however, has been willing to go further. In interviews, in lectures, in popular presentations of Orshaw, he has explored the implications of the theory for questions that Penrose approaches more guardedly, and those implications are extraordinary. Consider the structure of the theory again. In Orshaw, consciousness is not produced by the brain. The brain does not generate experience the way a factory generates products. Instead, the brain is a system that organizes quantum coherence, orchestrates superpositions, creates the conditions under which objective reductions occur at particular times and places. The consciousness that results from these reductions is not manufactured by the neurons, it is accessed. It flows from the Planck-scale proto-consciousness that inheres in the geometry of space-time itself. The brain, in this picture, is less like a generator and more like a receiver, less like a factory and more like a radio. The program is not created by the radio. The program exists independently, broadcast from elsewhere, carried by electromagnetic waves that fill the air regardless of whether any receiver is tuned to them. The radio selects, amplifies, translates. It converts invisible electromagnetic patterns into audible sound. But the radio does not create the program, and if you smash the radio, the program does not cease to exist. It continues broadcasting. It is simply no longer being received at that location. This is a metaphor, and metaphors can mislead. Hameroff knows this. Penrose would certainly insist on this. The brain is not literally a radio, and consciousness is not literally a broadcast signal. But the metaphor captures something important about the structure of the theory. In Orshaw, the fundamental conscious experience is not local to the brain. It is woven into the fabric of space-time itself. The brain's role is organizational, not generative. It creates the conditions for particular patterns of experience to manifest, but the experiential capacity itself comes from below, from the Planck scale, from the deepest level of physical reality. And if that is true, if consciousness is fundamental rather than emergent, if it is accessed rather than produced, if the brain mediates experience rather than creating it, then the termination thesis loses its obviousness. When the brain dies, the organizational structure fails. The orchestra stops playing. The microtubules cease their coherent vibrations. The objective reductions no longer occur in that particular pattern. But the Planck scale, proto-consciousness, from which those experiences drew, does not cease to exist. It cannot cease to exist. It is woven into space-time itself. It is as permanent as geometry. What happens, then, to the conscious experience that was organized by that particular brain? Where does it go? Does it go anywhere? These questions venture beyond physics into territory that science, by its nature, may never be able to map. But Hameroff has suggested, tentatively, speculatively, that Ocher opens possibilities that the termination thesis forecloses. One possibility is dissipation. The quantum information that constituted a particular conscious experience simply disperses back into the quantum vacuum, losing its organization, returning to the undifferentiated proto-consciousness of the Planck scale. The individuality dissolves. The particular pattern that was you spreads out, becomes diluted, is eventually lost in the infinite sea of space-time geometry. This is not survival in any meaningful sense. It is a kind of return, like a wave returning to the ocean, like a raindrop returning to the sea from which it evaporated. The water persists, the particular raindrop does not. But there is another possibility, one that Hameroff has discussed more frequently. Quantum information, unlike classical information, has strange properties. It can become entangled. It can exist in superposition. It can, under certain circumstances, persist in ways that classical information cannot. The patterns that constitute a conscious experience, the particular configuration of quantum states in the microtubules, the specific correlations that give rise to a unified field of awareness. These patterns are quantum patterns. They are not merely classical arrangements of matter. They are arrangements of quantum information, and quantum information has its own rules. What if, Hameroff has asked, the quantum information that constitutes consciousness can persist after the death of the brain? Not floating around as a ghost, not inhabiting another body, but existing in some form in the quantum structure of reality itself? The space-time geometry from which consciousness flows does not disappear when a brain dies. It is still there, still structured, still containing whatever proto-conscious properties it contained before. Could the particular patterns that constituted an individual consciousness leave traces in that geometry? Could they persist in some form, entangled with other quantum systems, maintained by the structure of space-time itself? These are speculative questions. Hameroff acknowledges this. Penrose, as far as I can determine, does not endorse these specific speculations. The theory of Ocher makes specific claims about the physics of consciousness, claims about microtubules, about quantum coherence, about objective reduction, about the role of space-time geometry. These claims are testable, or will be testable as technology advances. But the question of what happens after death pushes beyond the theory's testable claims into territory where physics becomes philosophy, where science becomes speculation, where the careful rigour of mathematical modelling gives way to the much murkier questions that humans have asked since they first became aware of their own mortality. And yet, the speculation is not arbitrary. It follows from the structure of the theory. If consciousness is fundamental rather than emergent, then the death of the brain is not the destruction of consciousness, but the disruption of a particular pattern of consciousness. If proto-consciousness inheres in space-time geometry, then that proto-consciousness does not depend on brains for its existence. If the brain mediates rather than generates, then the failure of the brain is the closing of a window, not the extinguishing of a light. I want to hold this distinction carefully because it matters. The production model and the mediation model lead to profoundly different conclusions about the nature of human existence. Under the production model, you are your brain. When your brain dies, you die. There is no you apart from the neural tissue that generates your experiences. The termination thesis follows as surely as any other physical fact. You begin, you persist, you end. The story has a clear structure, a clear conclusion, no continuation. Under the mediation model, you are something more complicated. You are a pattern of quantum information organised by a brain, drawing on Planck-scale proto-consciousness, existing at the intersection of biology and fundamental physics. When your brain dies, the pattern is disrupted. But whether that pattern is destroyed or transformed or dispersed or maintained in some other form, these questions do not have obvious answers. They depend on details of physics that we do not yet understand. They may depend on aspects of reality that our current scientific framework cannot even formulate. Hameroff has pointed to near-death experiences as suggestive evidence. Millions of people, across cultures, across centuries, have reported experiences while clinically dead or dying. Experiences of light, of tunnels, of encounters with deceased relatives, of profound peace, of leaving the body and observing it from above. The standard neuroscientific explanation for these experiences involves oxygen deprivation, the release of endogenous hallucinogens, the disorganized firing of dying neurons. The experiences are real experiences, but they are generated by a malfunctioning brain, not windows onto any transcendent reality. They are the neural equivalent of static on a television set, not a signal from elsewhere. But Hameroff has suggested that Orkor offers a different interpretation. If consciousness flows from Planck-scale geometry, and if that geometry is not localized in the brain, then the experiences reported by those who have been near death might not be hallucinations. They might be what consciousness experiences when it is partially decoupled from its biological medium. They might be glimpses of a mode of existence that does not depend on the brain's organization. They might be real. I want to be very careful here. Near-death experiences are extraordinarily difficult to study scientifically. Reports are retrospective, subjective, shaped by cultural expectations, filtered through the distortions of memory. The correlation between reported experiences and measurable brain states is hard to establish. The people who have the most profound experiences are often those who are closest to death, which means their brains were most compromised, which makes it hardest to determine what was actually happening in their neural tissue. The evidence is tantalizing but not conclusive. It suggests possibilities without demonstrating actualities. And there are critics who argue that Hameroff has let wishful thinking contaminate his scientific reasoning, that the appeal of Orkor lies partly in its amenability to spiritual interpretation, that the theory scratches an itch that science proper cannot reach, the itch of mortality, the desperate human desire to believe that death is not the end. These critics suggest that the enthusiasm for quantum consciousness theories comes not from their scientific merits, but from their emotional appeal. They promise something that materialism denies. They open doors that reductionism closes. They offer comfort where strict physicalism offers only termination. This criticism must be taken seriously. Science is a human activity, conducted by human beings who have human hopes and human fears. The desire for death not to be the end is one of the most powerful human desires. It has motivated religions, shaped cultures, consoled the dying, comforted the bereaved. If a scientific theory happens to align with this desire, we must be especially careful in evaluating its evidence. The risk of motivated reasoning is high. The temptation to believe is strong. The standards of evidence must be correspondingly strict. And yet, the criticism can cut both ways. If we must be suspicious of theories that tell us what we want to hear, we must also be suspicious of our suspicion. The termination thesis is not emotionally neutral. For many people, the idea that consciousness ends with the brain is itself deeply comforting. It promises release. It promises that suffering has a limit. It promises that the worst that can happen to you is simply ceasing to exist. For those who fear what might come after death more than they fear death itself, the termination thesis is a relief. It closes a door that they do not want open. So both possibilities, survival and termination, carry emotional weight. Both align with certain human hopes and fears. Neither can claim to be the emotionally neutral default. The scientific question must be decided on scientific grounds, not on the basis of which answer we find more comforting or more disturbing. And on scientific grounds, the question is not yet decided. Orkor makes testable predictions about consciousness. Those predictions can be checked. If they are confirmed, the theory gains credibility. If they are falsified, the theory must be revised or abandoned. The deeper implications of the theory, what it means for death, what it suggests about survival, what it implies about the relationship between individual consciousness and the underlying structure of reality. These implications follow from the theory but cannot be tested directly. They're consequences of the physics, not themselves physics. Penrose, I suspect, would insist on this distinction. The physics is primary, the mathematics is primary, the testable predictions are primary. Everything else is interpretation, speculation, metaphysics. A physicist can develop a theory and leave the metaphysical implications to others. The physics speaks for itself. The equations do what they do. What they mean for the human condition is a separate question, perhaps not a scientific question at all, but for those of us who are not physicists, who are merely conscious beings, trying to understand our own consciousness, the metaphysical implications are not secondary. They are the reason we care. The physics is fascinating, the mathematics is beautiful, the neuroscience is compelling. But what drives the human interest in consciousness is not academic curiosity. It is the personal stakes. Each of us is a conscious being who will one day cease to be, or who will one day undergo some transition whose nature we cannot currently determine. The question of what consciousness is cannot be separated from the question of what our consciousness will become. The recovery room is quiet now. The patient sleeps, genuinely sleeps, her brain cycling through its rhythms, her microtubules doing whatever microtubules do. Outside, the night deepens. The city lights thin as the late hours arrive. Somewhere in an office or a home or a hospital, someone is dying. The orchestra that organised their consciousness is playing its final measures. The coherence that maintained their experience is failing. The objective reductions are becoming less frequent, less organised, approaching some threshold beyond which they will not return. What happens next? The termination thesis says, nothing. The production model says, the product ceases when the producer fails. But Orkoa, if it is correct, says, the story is more complicated. The consciousness that was organised by that brain drew on something deeper than the brain itself. It was a pattern in the Planck scale geometry of space-time. It was a particular way of accessing the proto-consciousness that inheres in the fabric of reality. When the brain fails, the pattern is disrupted, but the proto-consciousness remains. The space-time geometry remains. And what becomes of the pattern itself, whether it dissipates, whether it transforms, whether it persists in some form we cannot currently imagine, these questions remain open. We do not know. That is the honest answer. We do not know what consciousness is, not fundamentally. We do not know why there is something it is like to be anything. We do not know whether the brain produces experience or mediates it. We do not know what happens when the brain stops. Orkoa offers one possible framework, one set of answers, one way of understanding the relationship between mind and matter that differs radically from the dominant materialist paradigm. But offering a framework is not the same as proving a framework. The theory must be tested, the predictions must be checked, the evidence must accumulate or fail to accumulate, and until it does, the deepest questions about consciousness, the questions that touch every human life, that give shape to our hopes and fears, that determine how we understand our own existence, these questions remain open. The patient in the recovery room will wake again. She will return to her life, her concerns, her projects, her relationships. She'll probably never think about microtubules or quantum coherence or the Planck scale. She will simply be conscious, as she has been conscious for her entire life, without understanding what that consciousness is or where it comes from. And decades from now, when her own life approaches its end, she will face the same question that every conscious being eventually faces. The question that Penrose and Hameroff have tried to answer with physics and mathematics and neuroscience. The question that philosophy has wrestled with for millennia. The question that every religion addresses in its own way. What happens next? The theory offers one possibility. The universe is not what we thought. Consciousness is not what we thought. The relationship between mind and matter is stranger, deeper, more fundamental than the production model suggests. And if that is true, if consciousness really does flow from the Planck scale geometry of space-time, if the brain really is a receiver rather than a generator, if proto-consciousness really is woven into the fabric of reality itself, then the story does not end where the termination thesis says it ends. There is more to the story. There must be more. Because the source of consciousness does not disappear when an individual brain fails. The source remains. The source is the universe itself. Or so the theory suggests. The experiments have not been done, The predictions have not been confirmed. The scientific community has not reached consensus, but the possibility is open, and for conscious beings who know that their consciousness will one day face whatever transition death brings, an open possibility is not nothing. It is a door that has not been closed, a question that has not been answered, a mystery that remains. And so we arrive at the final question. The question that has been waiting beneath every experiment, every calculation, every philosophical argument we have examined together. Not whether Aucture is true, that remains genuinely uncertain, a matter for future science to resolve, but what it would mean if it were true, what kind of universe we would inhabit, what kind of beings we would be. Let us sit with this carefully, because the implications reach further than any single theory about neurons or quantum mechanics. They reach into the structure of reality itself, into the nature of time and causation and meaning. They touch the deepest assumptions we carry about what kind of story we are living. Begin with the simplest implication, and let the others unfold from it. If Aucture is correct, then consciousness is not an accident. It is not an evolutionary afterthought, a strange byproduct that happened to emerge when brains became sufficiently complex. It is written into the laws of physics at the most fundamental level. The same mathematical structures that govern the behavior of particles and fields and space-time geometry also govern the emergence of experience. Consciousness is as natural, as inevitable, as basic as gravity. Stop and feel the weight of that. In the standard materialist picture, consciousness is fragile, rare, possibly unique to Earth, possibly unique to carbon-based life, possibly destined to flicker out when the last stars die and the universe winds down into heat death. We are lucky accidents in a vast, uncaring cosmos. The universe was unconscious for 13.8 billion years before our ancestors evolved the neural complexity to become aware. It will be unconscious for untold billions of years after our species is gone. But in the Aucture picture, the universe has never been unconscious. The proto-experiential properties are there in every quantum process, every superposition, every objective reduction event. They were there in the first microseconds after the Big Bang. They were there in the cores of the first stars. They were there in the molecular clouds that would eventually become our solar system. The capacity for experience is not something that had to evolve from nothing. It was always there, waiting to be organized, waiting to be concentrated, waiting to be amplified into the coherent, unified experience that you're having right now as you listen to these words. You're not a miracle of emergence in this picture. You're a concentration of something that was already present, a particular organization of proto-conscious elements into a unified experiential structure, the universe recognizing itself through you. Now follow this thread further. If consciousness is fundamental, if it is woven into space-time geometry at the Planck scale, then it's not dependent on any particular physical substrate. Biological neurons organize it in one way, but there is no reason in principle why other structures could not organize it differently. The question of artificial consciousness, which seemed so intractable under production models, becomes a question of whether computational systems could access the same Planck-scale processes. Under Aucture as Penrose and Hameroff have developed it, the answer is probably not, because digital computers manipulate classical information, not quantum superpositions. But the question itself takes on a different character. It is no longer about whether complexity generates consciousness, but about whether particular physical architectures can tap into the pre-existing proto-consciousness. The answer might still be no for silicon chips, but it would be no for a different reason. Not because consciousness is mysteriously produced and we do not know how, but because the right quantum coherent processes are not present. This has implications that ripple outward. It means that the question of consciousness elsewhere in the universe, in other planetary systems, in other galaxies, is not simply a question about whether evolution has produced sufficient neural complexity. It is a question about whether the right quantum biological structures have emerged, microtubules or their functional equivalents, coherent quantum processes at biological temperatures, orchestrated objective reduction events. The universe might be full of complex information processing systems that are nevertheless dark, unconscious, running sophisticated algorithms without anyone home. Or it might be full of conscious beings organized around principles we cannot currently imagine. We do not know. But the question itself is better defined. Now go deeper still. If consciousness is fundamental, then the hard problem is not a problem at all. It is a pseudo-problem generated by starting from the wrong assumptions. We asked how experience could possibly arise from non-experiential matter. The question seemed unanswerable because it was built on a false premise. The premise that matter is fundamentally non-experiential. Once you grant that proto-consciousness is present at the base level of physics, the mystery dissolves. Not because we have explained consciousness in terms of something simpler, but because we have stopped trying to explain it in terms of something that could not possibly produce it. We have accepted that experience is a basic feature of reality, like mass or charge or space-time curvature. It does not need to emerge from something more fundamental. It is as fundamental as anything gets. This is what Penrose means when he suggests that physics is incomplete. The current framework of physics describes the quantitative, structural, mathematical properties of reality. It tells us what things do, how they relate, what patterns they follow. But it is silent about qualities, about what things are like from the inside, the redness of red, the painfulness of pain, the felt character of experience. These qualities exist, you know they exist, you're experiencing them right now. But they do not appear in the equations. This suggests either that the equations are incomplete, or that the qualities are somehow identical to the quantities in ways we do not yet understand. Ortcore suggests the former. It suggests that a complete physics would include proto-experiential properties at the fundamental level, and that these properties would transform our understanding of what matter actually is. Matter is not dead stuff. It never was. That conception, the conception that dominated Western science for centuries, was always an abstraction, a model, a way of bracketing certain features of reality so that we could focus on the ones we knew how to quantify. It was useful, it was powerful, it gave us modern technology, modern medicine, modern understanding of the physical world, but it was never the whole truth. It was a map, not the territory, and the territory includes experience. The territory is experience at some deep level, all the way down. Now we come to the hardest implication. If consciousness is fundamental, and if the brain is a receiver rather than a generator, then the materialist assumption that death is the end of experience is not established. It is not proven. It is not the obvious, sensible, scientifically mandated conclusion. It is an assumption based on a particular theory about the relationship between mind and matter, the production theory, and that theory may be wrong. Let us be precise about what Ortcore does and does not say about this. It does not say that individual consciousness survives death intact. It does not say that you will wake up after your body fails and find yourself in some other realm. It does not say that personal identity continues, that memories persist, that the narrative of self carries forward. These are not implications of the theory. Penrose and Hameroff have been careful not to overclaim on these points. What the theory does say is this: the source of consciousness does not cease to exist when a particular brain stops functioning. The proto-consciousness at the Planck scale was there before that brain was born. It will be there after that brain dies. The space-time geometry that carries the proto-experiential properties is not dependent on any individual organism. It is the fabric of reality itself. What happens to the particular pattern of consciousness that was organized by a particular brain? This is where the theory reaches its limits. We do not know. The pattern might simply dissipate, the way a wave dissipates when the pond goes still. The organization is lost, even though the water remains. The individual experience might end, even though the substrate of experience continues. Or something else might happen. The pattern might transform, it might redistribute, it might persist in ways we cannot currently detect or describe. The honest answer is, we do not know. But the important point is that this uncertainty is genuine. It is not the false uncertainty of the atheist who says, we cannot know for certain, while privately being quite sure that death is the end. It is not the forced uncertainty of the believer who says, no one can prove otherwise, while privately being quite sure that consciousness continues. It is scientific uncertainty, the kind that can be reduced by future evidence, the kind that might eventually be resolved. Imagine a future science that understands consciousness the way we currently understand electromagnetism. A science with precise equations, detailed measurements, testable predictions about the relationship between quantum processes and experiential states. Such a science would be able to answer questions we cannot currently answer. It would be able to say what happens to conscious patterns when the biological structures that organize them fail. It would be able to distinguish between theories that predict continuation and theories that predict termination. It would be able to test those predictions. We are not there yet. We may never get there. Consciousness may be permanently mysterious, closed to scientific investigation in some fundamental way. But Orhor opens the possibility that we are not permanently locked out, that the hard problem can be addressed empirically, that the question of what happens after death is not purely metaphysical, but partly physical, and that physics might eventually have something to say about it. This is not a small thing. For most of human history, questions about consciousness and death belonged to religion and philosophy. Science stayed silent. Scientists were trained to stay silent. These were not proper scientific questions because there was no conceivable way to test theories about them. They were not even meaningful questions under certain philosophical frameworks. The positivists said, if a question has no empirical consequences, it is not a real question. And questions about the nature of subjective experience, questions about what happens to consciousness after death, seem to have no empirical consequences at all. Orhor changes this, not completely, not definitively, but enough to crack the door open. If consciousness depends on specific quantum processes, then we can study those processes. If those processes have measurable signatures, then we can detect those signatures. If theories make different predictions about those signatures, then we can distinguish between theories. And if theories that predict continuation make different empirical predictions from theories that predict termination, then we can, in principle, eventually, perhaps centuries from now, bring empirical evidence to bear on the deepest questions about existence. Perhaps this is the most profound implication of Orhor, not any specific claim about microtubules or anesthesia or quantum coherence, but the suggestion that consciousness is a proper subject for physics, that the hard problem is a physics problem, that the questions we care about most, who we are, what happens to us, are not beyond the reach of science. They are simply beyond the reach of science as currently practiced. A more complete science, a science that includes experiential properties at the fundamental level, might have answers, or might not. The uncertainty is genuine, the outcome is not predetermined, the experiments have not been done. And this brings us back, finally, to Roger Penrose and Stuart Hameroff, to the two men who have spent decades developing, defending and refining a theory that most of their colleagues dismiss, who have endured the criticism, the mockery, the professional marginalization, who have persisted not because they are cranks or zealots, but because they genuinely believe they have identified something important, something that the mainstream has overlooked, something that could transform our understanding of mind and matter and the universe we inhabit. Penrose is 93 years old now. He has received the highest honours a physicist can receive. His work on black holes and space-time geometry is celebrated throughout the world. He could have rested on those achievements. He could have spent his final decades enjoying the recognition he earned through his earlier work. Instead, he has continued to push into territory that brings him more criticism than praise. He has continued to argue that quantum mechanics requires new physics, that consciousness cannot be computed, that the brain accesses Planck-scale processes that current science does not understand. Why? Because he believes it is true, because the arguments seem compelling to him, whatever his colleagues say, because he would rather be right and ignored than wrong and celebrated. Hameroff has faced even more criticism, because his claims are more specific, more testable, more vulnerable to empirical refutation. Every experiment that fails to find quantum coherence in microtubules is a challenge to his position. Every anesthesiologist who points out alternative mechanisms for anesthetic action is raising a valid concern. Every biophysicist who calculates decoherence times is highlighting a potential problem, and yet he persists. He refines the theory. He addresses the objections. He designs new experiments. He collaborates with quantum physicists to develop more sophisticated models. He maintains that the theory is testable and that the tests will eventually vindicate it. Are they right? We do not know. The honest answer is, we do not know. But consider what is at stake. If they are wrong, then we have learned something valuable. We have learned that this particular path does not lead where we hoped. Science advances through failure as much as through success. A theory that is tested and found wanting is not a waste. It is a contribution. It narrows the space of possibilities. It tells us where not to look, and if they are right, if the brain really does sustain quantum coherent processes, if consciousness really does involve objective reductions at the Planck scale, if the hard problem really can be addressed by recognizing proto-experiential properties in the fabric of space-time, then everything changes. Then consciousness is not an accident but a feature. Then experience is not a mystery but a subject for physics. Then the relationship between mind and matter is not opaque but investigable. Then the question of what happens after death is not closed but open. Then the universe is not the dead mechanical system that classical physics described, but something stranger, richer, more saturated with experience than we ever imagined. Then Penrose and Hameroff will have done something that almost never happens in science. They will have opened a door that everyone else said was locked. They will have asked a question that everyone else said was meaningless. They will have proposed an answer that everyone else said was impossible. That is the possibility that justifies the decades of work, the thousands of pages of papers, the countless lectures and debates and responses to critics. Not the certainty of being right, but the possibility, the chance, the opening. And here, at the end of our journey together, we return to where we began. You are still listening. You are still conscious. Something is happening inside you, inside the 3 pounds of tissue behind your eyes, inside the microtubules of your neurons, inside whatever substrate ultimately supports your experience. You are aware. You know that you are aware. And you know that someday, perhaps decades from now, perhaps sooner than you expect, that awareness will face some kind of transition. What kind of transition? We do not know. The brain will fail. The neurons will stop firing. The quantum processes, whatever they are, will cease to be organized in the way they are organized now. And then, the production model says nothing. The receiver model says something, but we cannot say what. Orc-OR says the source of consciousness remains even when the individual pattern is disrupted. What becomes of the pattern is uncertain, but the source was there before you were born. It will be there after you die. You were always part of it. You will always be part of it. Because it is the universe itself, and you are the universe becoming aware of itself, temporarily organized into this particular form, this particular pattern, this particular point of view. Also, the theory suggests the experiments have not been done, the predictions have not been confirmed, the scientific community has not reached consensus. Orc-OR might be wrong. It might be right in some respects and wrong in others. It might be pointing in the right direction without having reached the final destination. But here is what we can say with certainty. The question is real. The mystery is genuine. Consciousness exists and we do not understand it. The hard problem has not been solved. The explanatory gap remains, and theories that take consciousness seriously, that treat it as a fundamental feature of reality rather than a puzzling byproduct, deserve to be heard, tested, evaluated on their merits. Penrose and Hameroff have offered such a theory. They have endured the criticism. They have refined the model. They have made specific predictions. They have invited empirical testing. Whatever the eventual outcome, they have done what scientists are supposed to do. They have looked at a deep problem, proposed a bold solution, and submitted it to the judgment of evidence. The rest is up to the universe, and to us. So as you drift toward whatever comes next, sleep or waking, or simply the continuation of your conscious life into the next moment and the next, carry this with you. The mystery of your own existence is not a closed case. It is an open investigation. The question of what you are, of where your experience comes from, of what will happen when your brain finally fails, these questions are not answered. They are not even properly asked, not yet, not by a science that has only recently begun to take consciousness seriously. But the asking has begun. The door has cracked open, and through that crack we glimpse something vast, something strange, something that might transform our understanding of who we are and what kind of universe we inhabit. A universe where consciousness is not an accident but a feature, where experience is not a byproduct but a foundation, where the deepest questions are not meaningless but investigable, where the mystery of your own existence points towards something fundamental about the fabric of reality itself. The patient in the recovery room has woken now. She is back in her ordinary life, untroubled by questions about microtubules and quantum coherence. She is simply conscious, as she has been conscious for her entire life, as she will continue to be conscious until the final transition. And somewhere, in laboratories and conference rooms and offices around the world, scientists are working on the question she does not think to ask. The question that every conscious being eventually faces. The question that has no answer yet. What is consciousness? Where does it come from? What happens when it stops? The theory offers one possibility. The universe awaits the evidence. And you are part of that universe. Part of that question. Part of that waiting. You are the mystery examining itself. You are the cosmos wondering what it is. Whatever comes next, for the theory, for the science, or for your own conscious existence, know this. The question is real. The mystery is genuine. And somewhere, at the deepest level of reality, something is aware. It might be the universe itself. It might be you. In the end, perhaps, they are the same thing. The campfire flickers in the dark. The pattern of flame rises and falls, dancing on the edge of coherence and chaos. And behind the flame, before the flame, beyond the flame, the darkness holds something. Something that was there before the fire was lit. Something that will remain after the last ember fades. We call it many things. The substrate, the source, the ground of being, the Planck-scale geometry, proto-consciousness, the fabric of reality. Or perhaps we call it nothing, because we do not yet have the words. The fire burns, the darkness waits. And somewhere between them, impossible and undeniable, the light of awareness continues, for now,